I will now start the live transcript. All right, so welcome back, everyone. So a lot of things going on today, as always. All right, so lots of things going on. Today, we're going to start chapter 2, sections 2.1 and 2.2. You could even do that homework. But the chapter 2 stuff will not be until midterm 2. It's really the third test, but this stuff here won't be until, I guess I should put it in red. So the chapters 2 stuff won't be until midterm 2. All right. Now, big day on Thursday. All right. Thursday, September 23rd. This Thursday is quiz 1B on chapter 1 only, but don't forget chapter 0. Okay. I have the right to test you on this, on the kind of stuff that you've seen on the chapter 1 homework, for example. So don't forget how to factor in all that stuff. So yeah, chapter 1 only in a way, but don't forget all your chapter 0, right? But the chapter 1 test will be on Thursday. Basically the same rules as before for quiz 1A, except that it'll be a shorter test. Okay. And it's on chapter 1. 10-minute break, then we'll continue with chapter 2. All right. Now regarding quiz 1A on chapter 0, I finally finished grading that just about an hour ago. And in the chat, I'm going to chat you your score out of 90 points. Okay. So I'll put that in the private chat, not public. I'll put in the private chat throughout the session. All right. Your quiz 1A chapter 0 test score out of 90 points. I'll put that in the chat privately. All right. Oh, by the way, day 8, these are the problems we did at the end of Thursday's session, so you can check that out on the class video. All right. Any questions? The test Thursday, same rules as before. It's on campus. All right. Any questions? Bring your homework for chapter 1 also. Any questions? Any questions? Again, in the chat, I'll put your score privately out of 90 points. Points, not percent. So your percent's a bit better than number, right? Okay. Like, for example, 80 points out of 90 is actually like 89%, right? Okay. All right. So let's start. I'll be putting your scores in the private chat. All right. Let's do this. Okay. Hi, everyone. So where are we? First off, as far as the notes go, starting in chapter 2, we're going to go back to my older online notes. They're not as polished as chapter 0 or 1, but they're more like concise classroom notes. Actually, some students prefer these. Now, as far as the material goes, where are we? Remember that in chapter 0, we focused on mechanics, the algebraic gymnastics. In chapter 1, we talked about general function theory and general theory of graphs. Now, in chapters 2 through 4, we're going to look at particular categories of functions. Particular categories of functions. In chapter 2, we're going to look at polynomial functions and more generally, rational functions. Back in 0.6, we had this Venn diagram for function expressions. So at the center, we have these polynomial function rules, and we're going to focus mostly on these for much of chapter 2. But then we're going to talk more, in 2.6 especially, about rational expressions in general. Remember that all polynomial functions are rational functions. For example, we can write this polynomial as this thing over 1. The key theme of chapter 2 is polynomial and rational functions. In fact, by the end of the chapter in 2.7, we're even going to discuss the domains of these radical functions. So we're going to creep into more general algebraic expressions by the end of the chapter. And then later on, in chapter 3, we're going to discuss exponential and log functions. Those are called transcendental functions. They're beyond the algebraic. And in chapter 4, we're going to talk about trig and inverse trig functions, our old friends. So again, in chapter 2, we're going to focus heavily on these guys, and then these guys, and a little bit of these guys. their domains. Chapter 3 with this and the log guys, chapter 4 with these guys. Okay, so let's proceed through this Venn diagram, these various categories of functions. Chapter 1, all apply. All right, any questions? Any questions? I'm putting your scores in chat out of 90 points. Any questions? Hi, everyone. In chapter 2, we're going to focus on polynomial functions and then rational functions more generally. Now, a particular type of polynomial function is a quadratic function. Remember, a quadratic function corresponds to a second-degree polynomial rule, such as this. And we're going to graph quadratic functions in chapter 2 as vertical parabolas. In chapter 2, we're going to graph only vertical parabolas, meaning that they either open upward or open downward. And there's a vertical axis of symmetry. So in chapter 2, we're only going to see vertical parabolas with vertical axes of symmetry. In chapter 7, we will look a little bit at these sideways parabolas, where we may have x as a function of y, but not vice versa. And in Calculus 2, Math 151 at Mesa, we're going to look, well, you're going to look at parabolas that are rotated at a 45-degree angle and such. That's for much later. But again, in chapter 2, we're going to focus on these vertical parabolas with these vertical axes of symmetry. So how do you graph these vertical parabolas in the xy plane? Well, you're going to graph something of the form y, or f of x, equals ax squared plus bx plus c. It's potentially a QT, a quadratic trinomial, although b and c could be 0. A, however, cannot be 0. If a is 0, you get a line. You don't get a quadratic, and you're not going to get a parabola. And we assume that these coefficients a, b, and c are all real numbers. Again, b and c could be 0, but a cannot be 0. The leading coefficient is especially important because it tells us whether the parabola opens upward, if the leading coefficient a is positive, or if the parabola opens downward, if the leading coefficient a is negative. So for example, on the left, we have the graph of y equals x squared minus 4x plus 5. Notice that the implied leading coefficient a is 1, which is a positive real number. The graph of that is over here on the left. So every parabola is going to have a turning point called a vertex. A parabola only has one vertex. In this case, the vertex is a local or relative minimum point because it's at the bottom of some valley. And in fact, it's the absolute minimum point for this parabola. It is the lowest point on the entire graph. There is no point with a lower y coordinate on the graph than this one. So this may be good news for cost, bad news for profit. The axis of symmetry is the vertical line that goes through the vertex. And this property of symmetry will be helpful when we graph parabolas. Remember, the idea of symmetry is that the left half of this parabola and the right half of this parabola are mirror images of each other about this axis. Now, likewise, if we have y equals the opposite of x squared plus 4x minus 3, we have a QT over here. It doesn't have to be a trinomial, but it is a quadratic trinomial. The leading coefficient a is -1, which is a negative real number. The graph of that is on the right. Now, because the leading coefficient a is negative, the parabola is opening downward. The turning point, the vertex, is the absolute maximum point on the entire graph. There is no point on the graph that's higher than this point. Once again, the axis of symmetry is the vertical line that passes through the vertex, and we have symmetry. So how do we find this magical point, this vertex? And unlike the center of a circle, the vertex of a parabola is actually a point on the graph. And we really want to know where it is. How can we find this vertex? There are at least a couple of ways of doing this, as we'll see. Any questions? Any questions? All right, go on. Hi, everyone. Let's play with Desmos. Let's enter y equals ax squared. But remember, you need shift 6 for exponent and then the right arrow to move out, plus bx plus c. And let's put in all 3 sliders for the parameters a, b, and c. If you vary a, that affects the shape. If a is negative, then it opens downward. If a is 0, then you get a line. You can vary b. And you can vary c. And notice that c only affects vertical shifting. We're going to make note of that. All right, now again, what's the most important point on the parabola? The turning point, the vertex. Where is it? So what's a recipe for finding the vertex of a parabola and the axis of symmetry? We'll look at an alternate method later on. The vertex of the parabola with equation y equals ax squared plus bx plus c, where a is non-zero, is given by the ordered pair h comma k. This is pretty standard notation, where the x-coordinate, or h, is given by this formula, the opposite of b over 2a. Does that sound familiar? The opposite of b over 2a. That's a piece of the quadratic formula, the QF. And there's a reason why, as we'll see. The y-coordinate, or k, is given by the corresponding function value. And that makes sense. Y-coordinates are function values. The idea is that if I give you y equals f of x, given an x-coordinate, well, given an x-coordinate, if we know the x-coordinate of the vertex, then we can plug into the given function rule to find the corresponding y-coordinate. Here it should be 1. Function values are y-coordinates. So here, this is the point h comma k. Here h equals 2. We plug in the x-coordinate, h or 2, to get the y-coordinate, which is k or 1, the function value. Function values are y-coordinates. The axis of symmetry is the vertical line containing the vertex. So it has equation x equals h. Instead of memorizing that, look at this picture. Well, if the vertex here has x-coordinate 2, the vertical line here has equation x equals a number. Well, that common number better be 2. The graph of an equation consists of all points whose coordinates satisfy the equation. The x-coordinate of every point on here is 2, including the vertex. Example. Consider the parabola given by y equals x squared minus 6x plus 5. Find the vertex and find the axis or axis of symmetry. So to find the vertex, let's use this QF type formula. The x-coordinate or h, is given by this formula, the opposite of b over 2a. It might be helpful to indicate the various parameters. What are a, b, and c? A is positive 1. There's an implied 1 over here. B is, careful, B is what? B is negative 6. Watch your sign. Watch your sign. And by the way, C is 5, but this formula doesn't care. Remember, when we just see, that does not affect the x-coordinate of the vertex. It only affects the vertical shifting. So this formula for the x-coordinate of the vertex, h, doesn't even care what c is. It's only dependent on a and on b. And notice that a cannot be 0. Remember, if a is 0, we get a line. Okay, so what's the opposite of b over 2a? Is the opposite of -6, not +6, over 2 times, and then a is 1. It's a double division. You divide by both. We end up with +3. So +3 is the x-coordinate of the vertex, h. What do we do to find the y-coordinate? Y-coordinates are what? Y-coordinates are function values. You work out f of 3. The y-coordinate, k. If it helps, you can think of y as being the k here, y as being k here, and x is h over here. The y-coordinate, k, is given by the function value at x equals 3. You plug in, you substitute into this thing over here. So we get 3 squared minus 6 times 3 plus 5. This time the 5 does matter. Of course, vertical shifting does affect the y-coordinate of the vertex, right? And we get -4. Y-coordinate, or k, is given by -4. Now remember, you have to write your final answer as an ordered pair. The vertex is given by the ordered pair 3, -4. And the axis is given by what equation? It's a vertical line. It's given by x equals 3. The same x-coordinate as the vertex. The axis, or axis of symmetry, has equation x equals 3. And in fact, well, and by the way, here's another important piece of information. A is positive 1. What does that tell us about the parabola? It opens upward. It opens upward. In fact, it has the same basic shape as y equals x squared. And in fact, make sure it passes the VLT. In fact, this might be all we need to know about the parabola. The fact that it opens upward, the vertex is at 3, -4, and the axis of symmetry is at x equals 3. That might be all we need to know about this parabola for all practical purposes. But if we want to do a better job of graphing this thing, what are some other points we might want to find? What are some other interesting points on the parabola, and maybe some other not so interesting points? And what property will help us find points on the parabola? Hint, hint. Next time. All right, any questions? Any questions? Sending out the scores in chat. What's going to help you, by the way? Alex, extra credit, plus 25, right? That's the idea. Hi, everyone. Let's refine the graph of y equals x squared minus 6x plus 5, our old friend. We saw where the vertex was, and we saw that it opened upward. But aside from the vertex, what are some other interesting points we might want to find? What's true for any graph in the xy plane? What points might we want to find? We might want to find the intercepts. And which intercept is normally easier to find? Y-intercept or X-intercepts? I'd say the Y-intercept. Because what do you do to find a Y-intercept? You set what equal to what? You set x equal to 0. You plug in 0 for x, and you evaluate f of 0. And what happens when you plug in 0 into the right side? It's an easy evaluation. What happens? These terms drop out, and you're left with the constant term, 5. F of 0 is 5, which means that the y-intercept is at the ordered pair 0, 5. Back in my day, we were lazy. We just said 5. You should say the ordered pair 0, 5. In general, if you have y equals ax squared plus bx plus c, then 0, c, where c is the constant term, that's going to be the y-intercept. Just as if you have slope-intercept form for a line. What was slope-intercept form for a line? It was y equals mx plus b. And once again, the constant term basically gave us the y-intercept, 0, b. Let's do a demonstration. Let's graph y equals x squared minus 6x. Here's y equals x squared minus 6x. It passes through the origin as the y-intercept. If we go y equals x squared minus 6x plus 5, moves it up 5 units. The y-intercept is now at 0, 5 on the blue graph. Now, how many y-intercepts can something like this have? How many y-intercepts can it have? It has to be exactly 1. There has to be a y-intercept because 0 is in the domain. There's going to be a point. But can we have 2 different y-intercepts? Is that possible? The answer is no, because then you're going to fail what test? The VLT. So this can't happen. There has to be exactly 1 y-intercept. However, think about x-intercepts. How many x-intercepts could a parabola have, a vertical parabola? Think about it. Well, you could have no x-intercepts, like a flying parabola. You could have 1 x-intercept. It bounces off the x-axis. The vertex is on the x-axis. Or you could have 2 distinct x-intercepts. And it turns out this guy will have 2 distinct x-intercepts. Find the x-intercepts, if any. Remember, there could be none. We could be in this case. We could have 1 or 2 also. How do we find x-intercepts? We plug in y equals 0. Or the function guy equal to 0. But wait a minute, that's harder. Why is it harder? Imagine plugging in 0 for y and solving for x. Why is that harder? It's harder because you have to solve an actual equation. You have to solve y, or f of x, equals 0 for the real solutions of x. Remember, only take real solutions. Only real zeros for the f function will correspond to the x-intercepts. Real zeros correspond to x-intercepts. Remember that from 1.2. So what are the real zeros of x squared minus 6x plus 5? One way to do it is to apply what formula? The quadratic formula, the QF, which we'll mention later. But it turns out that this QD can be factored nicely. How do we factor it? Remember, we're setting y or f of x equal to 0 to find the x-intercepts. We can factor this QD, and it turns out to be the factor x minus 5 times the factor x minus 1, or vice versa. The zeros are therefore 5 and 1. Which means that the x-intercepts are going to be at the ordered pair, 1, 0. Remember, they should be ordered pairs. And the numbers here are x-coordinates. Also, we have an x-intercept at 5, 0. So we're going to have here 2 x-intercepts. Now, we're in this case over here. We have 2 x-intercepts. But can you give for me an example where we're going to have no x-intercepts? What's an example of a graph that's going to look more like that? And I'll give you a hint. Can you think of an expression in x that has no real zeros? No real zeros. Here's a hint. Here's y equals x squared. It has 1, 0 at x equals 0. In fact, that's an example of the 1 x-intercept case. Y equals x squared. That has exactly 1 x-intercept. But what could you do to the parabola to make sure it has no x-intercepts? You could, for example, add 1. Notice there are no x-intercepts. And why is that? Because x squared plus 1 has no real zeros. There are no real values for x that will make this whole thing equal to 0. I doesn't count. All right. So we found the x-intercepts. We mentioned the example y equals x squared plus 1 that has no real zeros and therefore no x-intercepts, right? Let's verify what we have so far. Okay, so y equals x squared minus 6x plus 5. Let's look ahead. Let's ask Desmos. So what is y equals x squared minus 6x plus 5? Okay, remember we got the vertex from before. We got the vertex at 3, -4. That's what we have so far, right? It's the turning point. the parabola opens upward. We have the y-intercept at 0, 5 up there. And we have two x-intercepts at 1, 0 and at 5, 0. By the way, don't be spoiled. We're not always dealing with integers, but here all these coordinates are integers. Hi, everyone. So far we have 4 key points on the graph. Okay, kind of a quick cut there. Any questions? Any questions? I think I've handed out all the scores in the chat. Again, Alex, plus 25. That's the idea, right? When is the hardest test of the semester? Okay, you can chat questions privately also. All right, any questions? Any questions?
I have a question, Professor.
Okay.
For the x coordinate of the vertex, h equals b negative b over 2a, is that the average of the roots?
That's right. And why is that? Where do you see that? Do you know a formula where that kind of comes from?
No, I just noticed that.
The quadratic formula. And I'm going to mention that. But it's a good observation. The opposite of b over 2a, that's the average of the roots from the quadratic formula. Very good. I'm going to mention that. The x-intercepts, right? Do you agree? The x coordinate of the vertex is the average of these x coordinates for these intercepts. That's not a coincidence. It's a good observation. Let's talk. The vertex or turning point, 3, -4, we have the x-intercepts at 1, 0 and at 5, 0. And we have the y-intercept at 0, 5. By the way, from 0, 5, can you see how we can get a 5th point for free by using what principle? The S word. I'll give you a hint. Here's x equals 3. That's the axis of what? It's the axis of symmetry. 0, 5 is 3 units to the left of that purple axis. Notice that if we walk 3 units further to the right, 6, 5 will also be on the parabola. And we get that 5th point for free by symmetry. On top of that, you can do some more point plotting. For example, if you plug in x equals 2, it turns out that 2, -3 is also a point on the graph. Therefore, by symmetry, 4, -3 is also a point on the graph. So you can do a bunch of point plotting. Again, we're lucky because these were all integer coordinates. But even without those 2 last points, with these 5 points alone, we can get a very good sense of what this parabola looks like. I'll erase the axis even. Well, let's keep the axis in, actually. So you should be able to do a good freehand graph of the parabola. And you would probably get something like that. Very good. Now, speaking of symmetry, I'd like to talk now about the 2 x-intercepts over here, the 1, 0 and the 5, 0. I'd like to talk about these 2 x-intercepts. Notice that the axis of symmetry is right in the middle between these 2 x-intercepts. And what special point lies on the axis? The vertex. Notice that the x-coordinate of the vertex, 3, the x-coordinate of the vertex, 3, which is the x-coordinate for this axis, is the average of the x-coordinates for the 2 x-intercepts, 1 and 5. 3 is the average of 1 and 5, and that's not a coincidence. Why is it that the x-coordinate of the parabola, h, why is it given by this formula, the opposite of b over 2a? Well, that came from what special formula? The quadratic formula. The zeros of the function are given by the quadratic formula, the QF. Now notice that if you take a look at this formula, there are 2 cases, a plus case and a minus case. Let's go back to the parabola over here. Now, when we found the 2 x-intercepts, what do? We set the function rule equal to 0. We did that up here. We set the function rule equal to 0. Now up here we used factoring, but another way we could have done it is to use the QF, the quadratic formula. We could have used the QF to solve this equation for x, and we would have gotten x equals 5 and also x equals 1. So the deal is that the quadratic formula gives us two cases, a plus case and a minus case. One case would give us 1, the other case would give us 5. What's the average of 1 and 5? It is 3, the x-coordinate of the vertex. What's the average of these two results, the plus case and the minus case from the QF? The average case is given by the opposite of b over 2a. Basically, to get the average of the plus case and the minus case, you destroy this piece of the quadratic formula. So the average of the plus case and the minus case is given by the opposite of b over 2a, just as the average of 1 and 5, the zeros of the function, that average is given by 3. So visually, it makes sense that the x-coordinate of the vertex, which is 3 here, I'll do this in purple, the x-coordinate of the vertex, which is 3 here, is given by the average of the numbers corresponding to the x-intercepts, 1 and 5. That's because the opposite of b over 2a is the average of the plus case and the minus case from the QF. Now, if there's just one x-intercept, well, great, the vertex is the x-intercept. So the discriminant is 0, right? And this part would drop off anyway. So the opposite of b over 2a, that would give the x-intercept and the x-coordinate of the vertex, h. But the funny thing is that even for a flying parabola, it turns out that the opposite of b over 2a will give the x-coordinate of the vertex even in that case, although it's not as easy to visualize why that's the case. But at this point, you should see why it makes sense that the opposite of b over 2a is the formula for h, the x-coordinate of the vertex, is the average of the x-intercepts if they're real. But see, it's the case even if they're not real. All right. Next up, what is another way that we can find the vertex?
All right, any questions? Any questions? So a question about the extra credit in there. Yeah, it's like the quiz 1A often spurs people to do the Alex extra credit. Hey, whatever it takes, the plus 25. Better late than never, right? And you know, if you, as long as you renew the license or get a longer license, then you know it's due by the end of the semester, right? Which is what, December, what is it, 16, 18, whatever, right? When is it? Okay, so when's the Alex stuff due? It's due Saturday, December 18th, right? Bear in mind, I don't work for McGraw-Hill. Okay, I'm not a salesperson, but Alex can be a really good system, as people have found. All right.
I have a question about this.
Okay, go ahead. I can barely hear you, but yeah, go ahead.
Is there some sense we can make out of the square root of b squared minus 4ac for the graph?
That's a discriminant. Basically, the whole formula comes from completing the square. You take ax squared plus bx plus c equals 0, and it's a completing the square method, basically. But yeah, that thing's a discriminant, right? B squared minus 4ac, that's a discriminant. It tells you what kinds of zeros you get, if they're rational, real, imaginary, right? So that's important.
Okay.
Right. Any questions? Any questions in chat or anything? All right.
Everyone, let's have Desmos experiment with this cutie form for the equation of a parabola. Y equals ax squared plus bx plus c, the descending powers form for the equation of a parabola. Now, if we vary a, we're varying the shape of the parabola. Notice that as a stays positive and increases, it gets steeper and steeper. If a is 0, then we get a line. That's not a parabola. If a is negative, it opens downward. But as we move away from 0, again, the parabola gets steeper and steeper. If we vary b, then we're getting both horizontal and vertical shifting, but we are retaining the shape of the parabola. The shape of the parabola is entirely determined by A and its orientation. But B can affect horizontal and vertical shifting, and C can affect vertical shifting. But bear in mind that both B and C affect vertical shifting. So A is very meaningful. It gives you the shape of the parabola and its orientation. But B and C, their impact is less clear. So although A is very meaningful, B and C are not as meaningful. Although it is true that there is an important application of C. Let's say C equals 4, for example. What does C tell us? It tells us where what point is. Y-intercept. But when you look at the descending powers form for the equation of a parabola here, A is very meaningful. It gives you shape and orientation. B is hard to interpret. And C, the direct purpose of C is to give us the Y-intercept. But otherwise, B and C work in concert to give us the shifts. So generally speaking, the parameters A, B, and C are a mixed bag in terms of their meaningfulness. So we might want a form where the parameters are more meaningful. And that's for next time.
Any questions? Any questions? Okay, so we're gonna finish 2.1, go to a break, and then do 2.2. Then I'll take some questions at the end. All right, questions. All right.
Hi, everyone. How can we get a more meaningful form for the equation of a parabola in the XY plane? Let's start with y equals ax squared. If A is positive, the parabola opens upward. If A is 0, we get a line. That's not a parabola. If A is negative, the parabola opens downward. But as we vary A over all non-zero real values, we get all possible shapes of the parabola and both possible orientations, opening upward or downward. So we get all possible shapes and both possible orientations of all vertical parabolas in the XY plane. But what if we want to allow for horizontal shifts by h units? We would then substitute x with what? Remember section 1.4. To get a horizontal shift by h units, we would substitute x with the quantity x minus h. So now, as we slide the value of h, that leads to horizontal shifting. So for example, if h equals 2, the vertex is at 2, 0. But what if we want vertical shifting? What do we do? If we want a vertical shift by k units, what do? We tack on a plus k, and then we get our vertical shift. If k equals 1, our vertex is at 2, 1. K affects vertical shifting. So together, by changing A and H and K, by varying these various values for these three parameters, we get all possible vertical parabolas in the XY plane. This is called vertex form or standard form. The standard form or vertex form for the equation of a parabola. It's given by y equals a times the square of x minus h all plus k. Now, when students write this out, they often forget the square. So when you write this out, you might want to write it as y equals a times the square of x minus h. Because students are so proud of the fact that they write x minus h that they then forget the square. Don't forget the square. All that plus k. Don't engage in wishful thinking. It's linear. It's not linear. It's quadratic. Vertex form. So this parabola has the same shape as y equals ax squared, but the vertex is at the point h comma k. The vertex for y equals ax squared has to be at the origin, 0, 0. But in general, for this form over here, the vertex is at the point h comma k. Basically, we have translated or moved or shifted the vertex and therefore the parabola h units horizontally and k units vertically. Now, you can use your algebraic magic and rewrite this in descending powers form. Y equals ax squared plus bx plus c. But perhaps the one advantage to this is the fact that c gives you what point? The y-intercept, which is not as clear from the vertex form. But otherwise, the vertex form is much more meaningful. A is meaningful in terms of shape and orientation. H and K give you the vertex. So these parameters are very meaningful. And by the way, do observe that the A in the vertex form here and the A over here in descending powers form, these are the same value. These are both the leading coefficient. They're both the coefficient on x squared in the end. So the A here is the same as the A here. So they have the same meaning. The leading coefficients are the same. Next, let's do an example on how to convert from descending powers form to vertex form.
Okay, so before we do that, any questions? Right, we're transforming y equals ax squared, right? A was the, sorry, I cut that top part at the beginning, right? A, if it's positive, right, opens up, negative opens down, A cannot be 0, right? And then transforming, translating, questions. All right, a couple more videos, then we'll take a break. We'll end 2.1.
Hi, everyone. Let's convert from this descending powers form for the equation of a parabola, y equals 3x squared plus 12x plus 11, into this standard or vertex form, y equals a times the square of x minus h all plus k. Don't forget the square. And we'll find the vertex. Now, look at this. We'd like to get here the square of a binomial. And when I see something like the square of a binomial, I'm thinking CTS. What does CTS stand for? Completing the square. That process that we saw with equations of circles back in 0.13. Remember, circles in 0.13. So what we're going to do is we're going to group the x squared and the x terms, and we're going to factor out a, which is 3 here. That's going to be our first step. Again, group the quadratic and linear terms. We're going to group together the 3x squared plus 12x, and we're going to separate out the plus 11. It's on its own. And then we're going to factor out a from this group. A equals 3, we factor out 3 from this group, but not the 11. When you factor, you divide. When you factor out the 3, you get 3 times the quantity, x squared plus 4x, and you have all of this plus 11. And don't forget the y equals over here. Now, bear in mind, you factor out a. You don't factor out the GCF. For example, we don't factor out the x. Also, what if we had had 3x squared plus 11x or 13x? You would still factor out the 3, in which case, instead of a 4, you might be getting 11/3 or something like that. And that's okay. You might get fractions. Don't be afraid of fractions. I was being nice here. When you divide 12 by 3, you get 4. I was being nice. Remember, you factor out a, that leading coefficient. If you end up with something like 11/3, too bad. You end up with 11/3. Okay. Now we're going to CTS, complete the square, and compensate. We have to pay for how we change the right-hand side. First of all, let's CTS. Let's complete the square. All right, so we take this coefficient on x, 4. It doesn't matter if it's positive or negative, but it is a positive 4. what do we do? Well, we take 4, and when we take half of 4, we get 2. Half of 4 is 2. And then what do? We square the 2. When we square the 2, we get 4 again, actually. So that means that in order to complete the square, we have to put a +4 inside the parentheses here, so that we end up with a PST. Remember, the goal is to make this thing a PST, a perfect square trinomial, so that it can be factored like this thing, the square of a binomial over here. But now wait a minute. We also have to compensate. We have to pay for what we do over here. We can't just throw in a +4 because we feel like it. And you have to be careful. How do we pay for inserting a +4 inside the parentheses here? A naive student might say, oh, well, I guess we subtract 4, which I would understand, but you're being a bit naive. Because here's the problem. When we insert a +4 here, notice that there's a 3 out in front. Before, when we dealt with circles, we made sure that the leading coefficient was 1. We don't have that guarantee now. A equals 3 here. And guess what? The 3 impacts the 4. If you insert a +4 inside the parentheses, what are you really adding to the right-hand side? Not just 4, but 3 times 4. So when you insert the 4 in there, remember, you're adding 3 times 4. You're really adding 3 times 4 by the distributive property. When you insert the +4, you're really adding 3 times 4. You're adding 3 times 4. And how do you pay for adding 3 times 4 or 12? You subtract the 3 times 4 or 12. But don't forget, the 4 is getting hit by the 3, so you have to take that into account. It's a very common error to forget that. So to compensate for this, you have to subtract not 4, but 12. You can put 12 here. So next, since we should have a PST here by now, we need to factor the PST so that it looks more like this, the square of a binomial. How do you factor this PST? X squared plus 4x plus 4. Well, it is the square of x, now that middle sign matters, plus 2. Basically half of that coefficient on x. So we get the square of x plus 2 over here. Over here, 11 minus 12 gets us a -1. All right. So we do the factoring. When we factor the perfect square trinomial, we get y equals 3 times the square of x plus 2, all minus 1. Right. Just for kicks, let's see if we got the right answer on Desmos. Y equals 3 times x plus 2, x plus 2 all squared minus 1. All right, so I claim that the given equation graphs as that. What was the given equation? It was y equals 3x squared plus 12x plus 11. Y equals 3x squared plus 12x plus 11. Yes, they overlap. This is a graphical demonstration of equivalence. So it looks like we've gotten the right answer here. It's not a proof, but it's pretty convincing. All right. Oh, and by the way, where is the vertex? Where's the vertex? What is h, the x-coordinate of the vertex? Remember, be careful. Because remember, it's the square of x minus h. X plus 2 is x minus what? It's x minus -2. And all that's getting squared. So h is actually -2. Okay, you actually have to flip the sign. Remember, the sign is surprising. X plus 2, you might think you're moving right by 2 units. No, no, no. Remember, sign surprise when it comes to horizontal shifting. horizontal shifting, the signs, surprise. H is -2, not +2. You're doing a shift left by 2 units. K, however, you just grab the -1. You're moving down 1 unit. The vertical shift is very straightforward. So the new vertex will be at -2, -1. Remember, there is a sign flip from here to here to get the X coordinate H, but there is no sign flip for K, the Y coordinate. So watch out. Again, here on the graph, you can see -2, -1 is in fact the vertex. Now, what's a way of seeing that X equals -2 leads to the vertex? In fact, one way to look at it is that X equals -2 makes this equal to 0. Remember that trick with the equation of a circle? Remember that the center of the circle, H comma K, made the left-hand side equal to 0. It made both of these square guys equal to 0. Similarly, you want the value for X or H that will make this square thing equal to 0. And why is that? Well, remember, when you look at this vertex here, right? The vertex here is the most extreme point on the parabola. In this case, it's the absolute minimum point. It's the most extreme point on the parabola. It's the lowest point. Well, look at this square thing here. What is this square thing at its most extreme? What is the most extreme value of a square? You could say it's 0, because if you keep it real, squares are never negative. Squares are never negative. The most extreme this can be is 0. Okay. The vertex is the most extreme point on the parabola. Notice that 0 is the most extreme a square can get. So it makes sense that the value for X that makes this square thing equal to 0 leads to the extreme point on the parabola, because 0 is the most extreme value for this squared expression. So the axis of symmetry is X equals -2. Remember, it's the vertical line that goes through the vertex. X equals -2, H over here. And A equals 3, that's positive. We know the parabola opens upward. A equals 3, which is positive, the parabola opens upward. Next up, we're going to do some modeling. Given some points, find the parabola passing through them.
Okay, any questions? Any questions? This is the last video before we complete 2.1. Then we'll take a 10-minute break, come back for 2.2, and we'll take questions on chapter 1.
Hi, everyone. Back in section 0.14, we talked about a classic problem with lines. Given 2 distinct points in the XY plane, find an equation for the line containing those points. Now, how many distinct points in the plane will determine a vertical parabola? 3. So, given 3 distinct points, find the equation of the parabola, the vertical parabola, that connects the 3 points. Now, bear in mind, the 3 points have to be non-collinear. Not only do they have to be distinct, they have to be non-collinear, meaning that they cannot lie on a straight line. There's no way that these 3 points will determine a parabola. Now, for the general problem involving 3 non-collinear points in the plane, you may have to solve a system of 3 linear equations in 3 unknowns using matrices, perhaps. That's chapter 8. But it would be very convenient if one of these 3 points were known to be the what of the parabola. If one of these 3 points were known to be the vertex of the parabola, V. In which case, in order to determine a vertical parabola, we just need one other point in addition to the vertex. Because remember, since there's an axis of symmetry, there's an implicit third point over here that's given for free. So if we know the vertex and one other point on the parabola, then again, we can get a third point by exploiting symmetry, but we don't even need that third point when we do the calculations. instead of going through some complicated thing with descending powers form, instead of having to deal with matrices, we can deal with the vertex form. Y equals a times the square of x minus h plus k. Once again, what do students forget? They often forget the square. They forget it's a quadratic, in part because they're so proud when they write x minus h in parentheses, they forget the square. Don't forget the square. Example, find an equation for the parabola, the vertical parabola, that has vertex 4, 2, and that contains the point 1, 29. So if you go to Desmos, all right, well, we're claiming that we need a parabola with vertex 4, 2, all right, 4, 2, that's right there. Now, we want this parabola to go through the point 1, 29. I don't see 29 in this y-axis, so I think we're going to need unequal axes in this case. So let's go to the wrench over here in the upper right. For y-axis, instead of from about -8 to +8, why don't we go from about -10 to +40, let's say. If you want, you could change the step size and have things where the tick marks are by 5s, the number tick marks, but we can stay by 10 for now. All right. We can add labels also, put y here and x here. We really should do that, actually. Label the axes. We really should do that. Okay. So where's the point 1, 29? Right there. I want the vertical parabola that has 4, 2 as a vertex, and that passes through 1, 29. This parabola is going to open how? Well, it's got to open up if it's a vertical parabola. So let's find the parabola that connects these dots with 4, 2 as the vertex. Okay, so here's vertex form. Well, I'm telling you what the vertex is 4, 2. H equals 4, k equals 2. So you can plug these in for h and k. So h equals 4. We still have the minus sign in front. K equals 2. So we have y equals a times the square of x minus 4, all plus 2. Now, we have values for 2 of the 3 unknown parameters, h and k. We now need to know the value for a. So how can we solve for a? There's another piece of information we can use up here. The fact that the point 1, 29 has to lie in the parabola. Remember the basic principle of graphing. The graph of an equation consists of all points whose coordinates satisfy the equation. So in order for this point to be on the parabola, x equals 1 and y equals 29 must satisfy this equation. Let's plug those values in. Plug in x equals 1, plug in y equals 29, and we get this over here. X equals 1, y equals 29. And now we can solve for a. 1 minus 4 is -3. The square of -3 is 9. So we get 29 equals 9a plus 2. If you had forgotten the square, you'd have had -3a. Don't forget the square. Okay, let's subtract 2 from both sides. We get 27 equals 9a. So a is what? Dividing both sides by 9, a equals 3. Again, a does not have to be integer, but here it is. We're not done yet. What do we have to do? We have to take this value for a. And just like with y equals mx plus b, just like with those variation problems from 0.16, you have to plug this in. Back to here. Remember, we now know h, we now know k, and now we know a. We can plug in 3 for a. And then from here, we get our final equation in vertex form. Y equals, remember, a equals 3 times the square of, don't forget the square of x minus 4, all that plus 2. Well, let's see if this works. Y equals 3 times x minus 4 all squared, all that plus 2. Yes, it does. Notice that 4, 2 is the vertex over here, and it passes through the point 1, 29 over here. Vertex of 4, 2 goes through 129. I guess it's good to flash the labels. And of course, it opens upward. A equals 3, which is positive. Very good. So we've done our modeling problem. All right, after this, what happens if we go beyond quadratics and parabolas?
All right, well, but now we're going to take a break. Well-deserved break. Come back for 2.2 and I'll take questions. All right, so we're going to take a break. Okay. All right. So our break will go from 8:06 to 8:16, and then I'll start pretty promptly at 8:17. All right, please mute. All right, see you in 10 minutes. All right, 8:17. Feel free to put questions in chat. Let's proceed. (2.2).
Hi, everyone. In section 2.2, we'll look at graphs of polynomials of degree 3, 4, and so forth. We'll discuss ideas of infinity and limits in our examples. Let's go straight to bowls and snakes. In the long run, non-constant polynomial graphs will look like bowls or snakes. So let's get straight to Desmos. Let's look at y equals ax squared. These are parabolas. If a is positive, they open up. If a is negative, they open down. Let's now look at y equals bx to the fourth. Again, these are bowls. They're not technically parabolas, but they're bowls. If the coefficient is positive, they open up. If the coefficient is negative, they open down. Notice that compared to the parabolas, these ax squared guys, notice that these green graphs, y equals bx to the fourth, they're steeper far away from x equals 0, but close to x equals 0. If you zoom in, actually, the green graph is flatter than the red graph. So notice that the higher the degree is, the flatter the graph is close to the origin. Far away from the origin, the green graph is actually steeper. And so forth. Y equals cx to the sixth. Again, bowls opening up or down. Flat, very flat, near the origin. For example, 1/2 to the sixth is very close to 0. So the graphs for y equals ax to the second, fourth, sixth, and so forth, where the exponents here are even and positive, the graphs of these are bowls. If a is positive, they open up. If a is negative, they open down. So for example, on the left, we have the graph of y equals x squared, f of x equals x squared. It's a bowl opening up. On the right, we have the graph of y equals the opposite of x squared. G of x equals the opposite of x squared. That's a bowl opening down. Now, in the homework, you're expected to be able to evaluate these kinds of long-run limits. Long-run limits. The limit of f of x as x approaches either infinity or negative infinity. Basically, when you're asked to evaluate a long-run limit, evaluating a long-run limit, then you're basically being asked the question, what are the y coordinates approaching on the graph as x approaches either infinity or negative infinity? That is, as we look towards the right forever and ever, in the case where x is approaching infinity, or in the case where we look left forever and ever, as x approaches negative infinity. We're asking, what is the y coordinate approaching in the long run as we look off to the right and as we look off to the left? These are what I call long run limits. And for these bowls and snakes, the answers to these limit questions will be either infinity or negative infinity if you're dealing with these kinds of polynomial bulls or snakes. Okay. So in the case of y equals x squared, f of x equals x squared, as x approaches infinity, well, as x goes off to a million, a billion, a trillion, what's happening to the y coordinates? The y coordinates are also approaching infinity. So the limit of f of x as x approaches infinity will be infinity. As we look off to the right, as x approaches infinity, the y coordinates also approach infinity. They increase without bound. Likewise, what's happening as x approaches negative infinity? What happens as x goes off to negative a million, negative a billion, and so forth? Well, as x approaches negative infinity, still the y coordinates approach infinity. This is because of symmetry. So in both cases, the long run limits will be infinity. Now, the phrase "go back to where you came from" is often taken as rude, but here it's very appropriate. If you look at things left to right, what's happening with this bowl? This bowl is coming down from infinity, is coming down from the heavens. And then over here to the right, it's going off towards infinity. It's returning to the heavens. So it's going back to where it came from as you look from left to right. And bowls have that property. Look at the graph of y equals the opposite of x squared, this g function. This time, as x approaches infinity, as we look off towards the right, the y coordinates are decreasing without bound. The function values are decreasing, negative a million, negative a billion, and so forth, towards negative infinity. As x approaches infinity, the y coordinates, the g of x values, approach negative infinity. Likewise, as x approaches negative infinity, as we look off towards the left, forever and ever, the y coordinates, the function values, are also approaching negative infinity. So again, these two match up. Bulls have that property where the two long run limits will be the same. They'll either be both positive infinity or both negative infinity. Again, if you look from left to right, we're going back to where we came from. We're coming up from down below, like hell, I guess. And then as we look left to right, we're returning to hell. We're going back to hell. We're coming up from hell and we're going down to hell. Right. And both have that property. Now, what about the graphs of y equals ax cubed and so forth? Let's take a look here. So y equals ax cubed. Okay, so that's going to be a snake here, right? If a is positive, we get a rising snake. If a is 0, that doesn't count. That's a flat line, y equals 0. If a is negative, we get a falling snake. Likewise, y equals ax to the 5th. Sorry, bx to the 5th. If b is positive, it's a rising snake. If b is negative, it's a falling snake. Again, similar to the situation with 4th degree versus 2nd degree before the bulls, the higher the degree, notice we're steeper far away from the origin, or x equals 0, out here and out here, but we're very flat. The green graph is flatter than the red graph as we get close to the origin. Similarly for y equals cx to the 7th. Rising snakes and falling snakes, steep far away from the origin, but very flat close to the origin. So here we have our snakes. On the left, we have the graph of y equals x cubed, the f function. On the right, we have the graph of y equals the opposite of x cubed, the g function. Now, answer the same questions that we asked before. What are the long run limits? I'll do this. So what is the limit of f of x as x approaches infinity? And as x approaches negative infinity? What's the limit of g of x as x approaches infinity and as x approaches negative infinity? What will be your answers here? Remember, the answer to these, when you're evaluating these long run limits, you're answering the question, what are the y coordinates approaching? And the answer to each of these will be either infinity or negative infinity. All right. So notice that with these snakes, you're running away from where you came from. So notice as you look from left to right, okay, you're coming up from hell, but then you're going up to heaven. Likewise, over here from left to right, you're coming down from heaven, and then you keep going down to hell. All right. So in the case of y equals x cubed, as x approaches infinity, the y coordinates also approach infinity. So as x goes to a million, a billion, a trillion, the y coordinates are going a million cubed, a billion cubed, a trillion cubed, and those are also approaching infinity. So that long run limit will be infinity. As x approaches infinity, this long run limit will be infinity. As you look to the left, negative a million, negative a billion, then you're talking about negative a million all cubed, negative a billion all cubed. Again, you're approaching negative infinity. So as x approaches negative infinity, the y coordinates also approach negative infinity. Notice that these are different answers. So to these long run limit questions, you're getting different answers. One's infinity, one's negative infinity. In the g case, it's switched. As x approaches positive infinity, g approaches negative infinity. And as x approaches negative infinity, g approaches positive infinity. But again, for these bowl and snake graphs for polynomial functions, in the long run, you're either going to get infinity or negative infinity for these two directions. Here you have a mix for these snakes. One's infinity, one is infinity, the other is negative infinity for these snake cases, because you're running away. Okay, next, we're going to talk about why, when we look at polynomial graphs, non-constant polynomial graphs, in the long run, we're basically dealing with a bull or a snake.
Okay, now I got to show you something. One of my favorite shows is Family Guy. You're going to see that.
Hi, everyone. Let's consider the graph of y equals f of x, which is 4x cubed minus 5x squared minus 7x plus 2. Now, two of these terms are immediately informative. The positive 2 tells us what? It tells us that the y-intercept for this graph will be at the point 0, 2. Because when you plug in x equals 0, these go bye-bye, and you're left with a constant term, 2. But more importantly, the leading or dominant term, 4x cubed, tells us a lot. This tells us what the graph basically looks like in the long run if we zoom out. Then we can figure out the long run limits for this function. That's why I call this the zoom out dominance property. The leading term basically tells us what's going on. So how do we graph y equals 4x cubed? because the graph of y equals 4x cubed will exhibit basically the same long-term, long-run behaviors as this over here. How do you graph y equals 4x cubed? It's going to be a rising snake. As x approaches infinity, as we look to the right, the graph goes up, up, up towards infinity. Y approaches infinity. As x approaches negative infinity, as we look to the left, the graph goes down, down, down. The y coordinates or function values approach negative infinity. And the same is true for the graph we care about. Notice that the y-intercept is at 0, 2. That's what that constant term tells us. But the leading term, 4x cubed, which is the same as this, it tells us that both of these graphs will have the same long-run behavior for all practical purposes. It might be more helpful if we have unequal scales. Let's make the x-axis more like -5 to +5. And the y-axis is going from like -40 to 40. Okay, this might be a bit more informative. You can see that in the long run, again, if you look at the red graph and the blue graph, the red graph and the blue graph, they both go up, up, up as x approaches infinity, and they both go down, down, down as x approaches negative infinity. They share the same long-run behaviors. Y equals x cubed is in blue here, and the graph we care about is in black. The graphs look similar in the long run. So here are the long run limits for both the 4x cubed function and also the function we care about. The limit as x approaches infinity, as we look off to the right, the y coordinates approach infinity for both graphs, Likewise, as x approaches negative infinity, the y coordinates, the function values, approach negative infinity. As x approaches negative infinity, the y coordinates, the function values approach negative infinity for both 4x cubed and the function we care about. The zoom out dominance property, that's my term. The leading term of a polynomial, f of x, increasingly dominates the other terms and increasingly determines the shape of the graph in the long run as x approaches infinity or as x approaches negative infinity. So if x is close to 0, then the blue graph exhibits some lumpiness, and that's determined by these two terms in the middle. The constant term just leads to a vertical shift, but there's more of a struggle here because of these two terms in the middle, and we get some lumpiness. We get a local max point up here, and we get a local min point down here because of these two middle terms. So if x is close to 0, basically, then these lower order terms can matter. But as x moves far away from 0, as x approaches plus or minus the millions, billions, trillions, the leading term is the term that really, really matters in the long run. And these lower order terms really don't matter at all. They barely matter at all. So if x is close to 0, the lower order degree terms can put up a fight for part of the graph, and we can get some local or relative maximum and minimum points, turning points. We do get turning points up here and down here. But in the long run, the leading term dominates. By the way, in calculus, you'll locate the turning points. By the way, one side note, if you have a special case like this, where you have, say, a 4th-degree polynomial that can be factored like that, then it might be better looked at as a translation problem. For example, y equals x to the 4th looks like that. Y equals x plus 1 all to the 4th. Basically exhibits the same behavior in the long run because it just corresponds to a horizontal translation. Okay, next up, let's talk more about turning points and the possible numbers of turning points for polynomials of various degrees.
Okay, any questions? Bowls and snakes. We're studying bowls and snakes.
Hi, everyone. How many turning points can a polynomial graph have? Let's take n equals 1, as a degree, first degree, n equals 2, second degree, and n equals 3, third degree. So how many turning points can a first degree polynomial graph have? A first degree polynomial means linear. How many turning points can a line have? Well, none. The graph can never turn around. 0 turning points, TPs. How do you graph a second degree polynomial? That's going to be a parabola. And how many turning points does it have? It has to have exactly 1 at the vertex. So we're going to have 1 turning point here. But now how many turning points can a third degree polynomial graph have? It depends. And in fact, we have a couple of examples here. The graph of y equals 4x cubed that has no turning points. We say that this function is monotonically increasing. It keeps going up, 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 up. This graph has no turning points, 0 turning points. But its partner over here, which is the graph we cared about earlier, this blue graph, it has 2 turning points. It has a local or relative maximum point, a hilltop point over here, and it has a local or relative minimum point, a valley bottom point over here. The red graph has 0 turning points. The blue graph has 2 turning points. So it depends. A third degree polynomial graph could have 0 or 2 turning points. It depends. Now, in general, only very high degree polynomial graphs can have many turning points. Only high degree polynomial functions can have very wavy graphs. In particular, the graph for a non-constant nth degree polynomial, y equals f of x, can have no more than n minus 1 turning points. So for example, if you have a polynomial graph with 99 turning points, then that means that the degree better be 100 or higher. Only high degree polynomial graphs can be very wavy and have many turning points. Now let's say we have an even degree polynomial graph. And it does matter very much if the degree is even versus odd. In the long run, what does a non-constant even degree polynomial graph look like in the long run? It has to look like a bowl in the long run. Now, it might be a little wavy in the middle, but in the long run, you're going to get a bowl, which means that ultimately you have to go back to where you came from. If you came down from heaven, you have to go back up to heaven. Which means that you have to have an odd number of turning points. The graph of a non-constant even degree polynomial must have an odd number of TPs. Because a bowl can turn around once, and then all future turning points have to come in pairs. If you turn around again, it has to turn around again. And then if it turns around again, it has to turn around again. So after the first turning point, all subsequent turning points have to come in pairs. So odd number of turning points. Could be 1, could be 3, could be 5, and so forth, depending on the degree. Hi, everyone.
Okay, any questions about the even degree case? Because the odd degree case is the other way, right?
How do you graph odd degree polynomial functions? What do they look like in the long run? In the long run, they look like snakes. Now, if you look at the graph of y equals x cubed, or for that matter, y equals x, there are no turning points. So you don't have to have any turning points. But if you do turn around, you better turn around again. So anytime you turn around, there better be a partner turnaround point. If you turn around again, you better turn around again. These have to come in pairs. So Here you could have 0 turning points, 2 turning points, 4 turning points, and so forth. The graph of an odd degree polynomial must have an even number of turning points. Notice the parities here are different. A parity means odd versus even. Oh, by the way, regarding odd degree polynomial graphs, they always have to have a real 0. Why is that? Why do odd degree polynomial functions always have to have a real 0? Because the graphs always have to have a what in the xy plane? A snake always has to have an x-intercept. An odd degree polynomial must have at least one real 0 because the graph must have at least one x-intercept. Good to know. So now there's a handy dandy algorithm for figuring out how many turning points you can have, because here's what you do. Find the possible number of turning points for a non-constant polynomial graph. Here's what you do. Polynomial graph of degree n. Here's what you do. You start with, now this is to get a list of the possible number of turning points. You start with n minus 1. That's going to be the possible number, the maximum possible number of turning points. Then keep counting down by 2s and stop before you hit negative numbers, because you cannot have a negative number of turning points. So for example, let's say you have a third degree polynomial, n equals 3. Well, you start with n minus 1, which is 2. Count down by 2. 2 minus 2 is 0. So you can have 2 turning points or no turning points. And of course, you cannot have negative 2 turning points. So you stop at 0. And that makes sense, right? We saw that. The blue graph had 2 turning points. The red graph had no turning points. These were both cubics, third degree. Why does this work? Well, 3 is an odd degree. And remember, for an odd degree polynomial, you have to have an even number of turning points. Well, if n is odd, n minus 1 is guaranteed to be even. These are all guaranteed to be even. And remember our rule from up above. Remember that for a non-constant nth degree polynomial, you can have no more than n minus 1 turning points. N minus 1 is the maximum possible. So when you list out the possible numbers of turning points, you start with n minus 1, the degree minus 1, and you count down by 2s. And of course, you cannot have a negative number of turning points. Now, what about a 6th degree polynomial graph? How many turning points can a 6th degree polynomial graph have? Again, let's use the algorithm. We begin with n equals 6. That's the degree, and it's even. So we start with, so to get our list of the possible numbers of turning points, we start with n minus 1, which is 6 minus 1, or 5. Notice that 5 is odd. Remember, an even degree polynomial graph has to have an odd number of turning points so that it goes back to where it comes from. Here we have 5 turning points. 1, 2, 3, 4, 5. There's some 6th degree graphs that do this. 5 is the maximum possible, and it's odd, so that's legal. And then you keep counting down. So we have 5. We start with 5. Count down by 2s. 5 minus 2 is 3. 3 minus 2 is 1. And we cannot go to negative 1. We cannot have a negative number of turning points. So a 6th degree polynomial graph could have 5 or 3 or 1 turning points. It's got to turn around at least once, otherwise it can't be a bull. So 5, 3, or 1. Remember, only high degree polynomial graphs can be very wavy. Here you have 1 turning point, here you have 3. And there are others with 5. So again, start with n minus 1, the degree minus 1, count down by 2s. Stop before you reach negative numbers. That's to get the list of possible numbers of turning points. As for which case you actually have, well, take calculus. And what are you going to look for in calculus? You're going to set the derivative equal to a certain number and solve for x. What is the slope of a horizontal tangent line? Notice at these turning points, these relative max and min points, you have horizontal tangent lines. The slope of the tangent line is the derivative. You want to set the derivative equal to, what's the slope of a horizontal line? 0. Set the derivative equal to 0, solve for x. And that's going to help locate these turning points. That'll be for calculus. Okay. Next up, we're going to talk about X-intercepts.
Okay, here we talked about turning points. Next, we're going to talk about X-intercepts, real zeros.
Hi, everyone. Last time, we talked about turning points for polynomial graphs. That's where the derivative is 0. But what about where the function itself is 0? Remember that the real zeros of f of x correspond to what points on the graph? The real zeros of a function correspond to what points on the graph? Remember, f of x, think y, where is y equal to 0? The real zeros of f of x correspond to the x-intercepts on the graph of y equals f of x. Real zeros of f of x correspond to the x-intercepts on the graph of y equals f of x. Y equals 0 at the x-intercepts. We want to find the real solutions for f of x equals 0. The x-intercepts correspond to the real solutions for f of x equals 0. X-intercepts correspond to the real solutions of f of x equals 0. All right. So the real zeros over here, over here, over here, and over here. It looks like this polynomial function has 4 distinct or different real zeros. Let's talk more about these. Zeros and the factor theorem. Now let's say that f of x is a polynomial in x, and it's not the 0 polynomial. It turns out that 2 is a 0 of this function if and only if x minus 2 is a factor of f of x. And therefore, there would be an x-intercept at 2, 0. Likewise, 3 is a 0 of f if and only if what is a factor of f of x? X minus 3, in which case, what will be an x-intercept? 3, 0. Now, negative 3 is a 0 of f if and only if what is a factor? X minus negative 3 or x plus 3. Negative 3 is a 0 of f if and only if x plus 3 is a factor of f of x, in which case we have an x-intercept at negative 3, 0. in general, if f of x is a non-zero polynomial and k is a real number, then k is a zero of f if and only if x minus k is a factor of f of x. That's the generalization of what we talked about over here. And also, remember that with turning points, for an nth degree polynomial graph, we could have at most n minus 1 turning points. Actually, we could have as many as n real zeros or n x-intercepts. An nth degree polynomial can have at most n real zeros and therefore n x-intercepts. All right. So for example, let's find a third degree polynomial function that only has 4 and -1 as zeros. All right. Now, first off, because 4 is a zero of this polynomial function, let's assume it's a polynomial in X. If 4 is a zero, then what has to be a factor? X minus 4 has to be a factor. If -1 is a zero, what has to be a factor? X minus -1 or X plus 1. Now, if we let f of x be this, will this satisfy the conditions here? Not quite, because what degree is this function here in purple? This would be second degree, and we're looking for third degree. So what can we do to up the degree? A lot of students would attach an x over here, but there's a problem with doing that. If you attach an x here, what else would be a zero? Then 0 would also be a zero, and that's not specified as a desired zero. So it's not appropriate to just attach an x. What would be another way to up the degree such that we're not throwing in any more distinct factors? We could square one of these. We could put the square over here, or we could put the square over there. Furthermore, we can multiply by a non-zero number. We could multiply by 2, by 3, by 4, by -100, whatever. In general, we can multiply by a, where a is a non-zero real constant. And again, the square can either go on this factor or that factor. And in fact, when you consider all these possibilities, this will represent all possibilities for third degree polynomial functions in X that only have 4 and -1 as zeros. These represent all the possibilities, where A represents any non-zero real number. So anything of this form or this form, A times the square of X minus 4 times the factor X plus 1, or A times the factor X minus 4 times the square of X plus 1. These forms only differ in which factor gets the square. Now, what are some differences, by the way? So over here in blue, what's going on with this blue polynomial? All right, well, you could say we have 3 real zeros for this third degree polynomial. Their names are 4, 4 again, and -1. I'm listing 4 twice because the exponent here is 2. And 2 here is called the multiplicity of 4 as a 0. So for this left form here, 4 is a 0 of multiplicity 2, corresponding to the exponent. That means that 4 comes in as a 0 twice. And you can think of this as the factor X minus 4 times itself. And then -1 is a 0 of multiplicity 1. -1 is a 0 of multiplicity 1 because the implied exponent here is just a 1. So there are 3 real zeros for this polynomial, but only two of them are distinct. There are only two distinct or different real zeros, the 4 and the -1. So if I just ask you to list out the real zeros, you can write them out with multiplicity. The 4 comes in twice. If I have something like x to the 10th, then 0 is a 0 10 times. 0 is a 0 of multiplicity 10. Look at that exponent. Likewise, what's happening over here? In green. Tell me about this green polynomial for any non-zero value of a. What are the real zeros? Well, same as before. There are 3 real zeros, but their names are 4, -1, and -1. This time it's the -1 that's repeated. And this time, 4 is a 0 of multiplicity 1, and -1 is a 0 of multiplicity 2. Corresponding to the exponents here, 1 and 2. All right. Now, why do we care? Why do we care? Because of the following principle. If you have a 0, a real 0, of odd multiplicity like 1, that means that at the x-intercept, remember, real zeros correspond to x-intercepts. That means that you get a cut there. If you have a real 0 of odd multiplicity like 1, then the x-intercept there has the graph cutting. The graph of y equals f of x cuts at that corresponding x-intercept. And I'll show you what I mean by a cut. Okay. Likewise, if you have a real 0 of even multiplicity, like 2 or 4 or 6, then the graph of y equals f of x bounces at that x-intercept. Basically, if you have odd multiplicity, the graph acts like a snake around that x-intercept. If the multiplicity is even, the graph acts like a bull and you bounce. So it's kind of like snake versus bull. All right, so let's take a look at these graphs. And if you want, you could expand them out. What do these graphs look like? All right. If I take the first case, the blue case, where a equals 1. If a is 2 or 3, that's just a stretching. Let's take a look. Now, as we look left to right, if we expand this out, the leading term is going to be x cubed. You could judge that from here as well. But you can tell even from here that the leading term is going to end up being x cubed, which means that overall, we're going to end up with what kind of shape? It's going to be a rising snake, which is going to go up, up this way, down, down this way. It's a rising snake. So what's going to happen? We go up to, all right, well, here's -1. At -1, we have an x-intercept. -1 is a 0 of multiplicity 1. Because the multiplicity is odd, what do? Do we cut or bounce? We cut because 1 is odd. We cut. The exponent is even on the factor. We cut. Now, I don't know where this graph peaks, but I do know it's got to fall down to earth because we have another 0 at x equals 4. So I don't know where it peaks, but it's got to come back. We get another x-intercept at x equals 4. The multiplicity there is even. The multiplicity there is 2. 4 is a real 0 of multiplicity 2. Now, because the 0 is even, that means that the graph is going to bounce off the x-axis. The graph's going to bounce off of the x-axis. All right, so the graph bounces. All right, It's a rising snake. It goes on, on. And this is a basic sketch of the graph. X-axis here, y-axis, but I don't know if the peak is going to be in quadrant 1 or quadrant 2. Let's see what Desmos says. Y equals the square of x minus 4 all times the factor x plus 1. So what's happening? The graph comes up from hell at 4, 0, and at -1, 0, there are x-intercepts. The graph comes up from hell at -1, 0. Exponent is 1. The graph cuts through the x-axis. It turns out the graph peaks here. We have a local max point in quadrant 1, but I didn't know if it was quadrant 1 or quadrant 2. On homework, I wouldn't expect you to know that. It turns out to be quadrant 1. That's where the derivative is 0. The graph comes down. We have another x-intercept at 4, 0. The exponent there is even though at x minus 4. Bounces, the graph goes up, up, up. Overall, we have a rising snake. Also, what else do we know? Well, if you plug in x equals 0, or if you expand it all out, you'll see that the constant term is 16. That tells us what? That tells us that 0, 16 is the y-intercept. So we know a lot about this graph. We know about the intercepts and the overall long-run behavior. That might be all we need to know. Now, question. Again, here's another version of this sketch graph. What if we put the square on the other factor? Right. So let's take a look at f of x equals x minus 4 to the first, and then x plus 1 with that squared. What is this going to look like? All right. If you expand it out, we get x cubed and then lower order terms. All right, overall it's going to be a rising snake again. Up, up this way, down, down that way. Again, we have x-intercepts at -1 and at 4. Now this time, as we go up to the x-intercept at -1, 0, since the exponent is even, the multiplicity is even, that means we do what? Do we cut or bounce? Since the multiplicity is even, we're going to bounce. We're going to bounce. So we bounce. If you plug in x equals 0, we end up with -4. So 0, -4 is going to be our y-intercept over here. The graph's going to turn around. I don't know if the graph turns around in quadrant 3, but let's assume it's quadrant 4, right? Comes back up, and then x equals 4, it happens. Well, since the graph's going to go up, 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 I think it's going to cut, and it's going to cut. 1 is odd multiplicity. That means we cut through like a snake. We bounce like a bull over here at -1. Here at x equals 4, we cut like a snake, and then up, up, up. And lo and behold, let's graph that. Y equals, it was x minus 4 times x plus 1, and that's squared. Yes, we have a rising snake overall. We go up to the point -1, 0. We bounce. We have the y-intercept at 0, -4. It turns out that the midpoint is in quadrant 4, not quadrant 3, but in calculus, you'll find that out. Then we go up, up, up. After the midpoint, we go up, up, up. And then at 4, 0, we cut. And then we go off, 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 like a rising snake. All right, so we know a lot about these graphs. And by the way, you're allowed to put a non-zero constant in front. What if we multiply by 2? Stretches the graph. By 3, by 4, and so forth, stretches. 0.5, that's a squeeze. 0.4, 0.3, 0.2, 0.1. That's a vertical squeeze, but still the X-intercepts stay the same. The X-intercepts stay the same, and we still have the same bouncing and cutting behavior and the snake behavior. What about a negative number? What happens? If I multiply by -1, what happens? Upside down. But same X-intercepts, and we still bounce here, we still cut there. But this time, it's a falling snake. And the Y-intercept also gets flip-flopped to 0, +4. Right. And then -2, -3, we stretch. But I put A out here, right? I have the same X-intercepts, same bouncing and cutting behavior, rising snake here, falling snake here. If I put the square over here, we get those other guys. And that corresponds to all, so let's do that. I'll put the square over here, cut this out, all right? Right. So we get all these guys. And together, these form all the possibilities that will satisfy these specifications. Third-degree polynomial function in X with only 4 -1 is zeros. We looked at all the possibilities. Wow. All right. And again, the even and odd multiplicities, they correspond to bulls and snakes, basically, locally around the X-intercepts. So the graph is kind of like a snake near -1, 0 here, and kind of like a bull, and kind of like a bull at 4, 0 over here. All right.
Any questions about this cutting and bouncing stuff? Because we know a lot about graphing. It's amazing if you know how to factor the thing. All right. This next video is like 1.5 minutes. It's optional, but it comes up in calculus. And then there's going to be a summary.
Next, a few final comments. Hi, everyone. Let's say you want to find a real zero for a 10th-degree polynomial function. One of the dirty secrets of mathematics is that we often have to use computer algorithms to help us approximate zeros of functions. So a computer spits out an approximation. Now, we don't have anything like the quadratic formula for 10th degree. We kind of do for 3rd and 4th degree, but nothing for 5th degree or beyond. So what could we do? Well, polynomial functions are continuous. The graphs are unbroken. So what we could do is the following. Let's say that we know that f of 2 is positive. The y coordinate here is positive. Let's say we know that f of 8 is negative. Then because the graph is unbroken, there has to be an x-intercept somewhere in between. There has to be a real zero. So what could we do? Split the difference, take the midpoint, test to see what f of 5 is. Let's say f of 5 is positive. Then we cut the search space in half. We now know that a real zero has to be between 5 and 8. And so forth. We can keep cutting the search space in half until we get an interval that's so tiny, we take the midpoint and go home. So that's kind of a dirty way of doing it, but that's a way of getting an approximation for a real zero. That's called the bisection method, because we keep bisecting and cutting the search space in half.
If you love this computer algorithm approach, approximations, you're going to love numerical analysis. That's what it's called in applied math, numerical analysis. At UCSD, they used to have a kind of a separate building for the applied mathematicians, like those and the statisticians. All right, a summary next, and I'll take questions.
Hi, everyone. So how do we graph polynomial functions? Well, you better know how to graph constant, linear, and quadratic functions. We've covered those. Also, some important points, intercepts. Y-intercepts are easier to find, plug in x equals 0, but for x-intercepts, you have to find the real zeros of the function. That can be harder. That involves solving an equation. Symmetry. If the function is even or odd, you may be able to exploit symmetry. The zoom out dominance property. Look at that leading term. Based on the leading term, do you know what kind of snake or bull you're getting? And you can determine long run behavior. Where is the function positive versus negative in value? So for example, let's say they are graphing something like this. You know that the leading term is x cubed. That means you have a rising snake. That means that you have to be negative in y coordinate way out here. You have to be positive in y coordinate way out here if you're going to have a rising snake, a polynomial rising snake. If you know the factorization, then you can really know what's going on. The real zeros correspond to the x-intercepts. We see here they're 4, -1. And these are the only places where the function can change sign. Remember, a polynomial function can only change sign at its zeros, corresponding to the x-intercepts. But does it have to change sign? Not necessarily, because the graph can bounce. So a polynomial function can only change sign, but doesn't have to. Can, but doesn't have to change sign at the x-intercepts or the real zeros. If the multiplicity is odd, then the graph cuts like a snake, and the function value, the y-coordinate, changes sign, here from negative to positive. If the multiplicity is even, then the graph bounces like a bowl off the x-axis, and we stay from positive to positive with 0 in the middle. So if you know what the leading term is, and if you know the complete factorization over the reals, then you should be able to know where the function is positive versus negative. And of course, it's 0 at the real zeros, the x-intercepts. When in doubt, there's point plotting as a last resort. And by the way, what is the range of any odd degree polynomial function? If you have 3rd degree, 5th degree, 7th degree, or 1st degree, what's the range? It's going to be all reals. You pick up all real values as y coordinates. Can an even degree polynomial function have the same range? No, there has to be some sort of extreme point. In the long run, it's a bowl. There has to be some sort of extreme point. That's all for now.
That's all. That's a lot of stuff, though, isn't it? That's sections 2.1 and 2.2. Well, you can do that homework, but I think you want to study for chapter 1, right? So, you know the drill, folks, because it's a lot like what happened last time. I'll see you in class, room MS 418. I'll emphasize that. Room MS 418. All right. So bring your stuff, your mask, your pencil, your scientific calculator, all that good stuff. Okay. So similar to last time, it's a shorter test though, 10-minute break. We'll continue with chapter 2. These were the problems we did at the end of the last class video. Are there any, now, first of all, are there any general questions regarding the Alex extra credit, regarding what's going to happen on Thursday? Any general questions? Any general questions? All right, let's go to specific questions. My whiteboards. Where'd I put them? Wow. Let's grab my whiteboards. All right. Oh, so that's already some stuff there. Yeah, we did some stuff at the end of 8, at the end of day 8. Right. Okay. So I'll see some of you, well, I'll see you all in person on Thursday. Some of you may be leaving now, but I'm sticking around in chat. All right. Any homework questions or just general sort of principal questions in chat? I'm opening up now for questions. So some of you, you'll want to go, and then I'll see you in class on Thursday for your chapter 1 exam, and I'll return your stuff, your chapter 0 exam, and hopefully your homework as well. Any questions on chapter 1 or chapter 2? But I assume you want to ask me chapter 1 questions. You got the homework? Are you all good? All right, I'll stick around.
I mean, I gotta stick around at least until 9:30, but I'm willing to go to 10:30. Any questions? Go ahead and flip through your homework. And remember, the old exam is online. Old exam should help. It won't be enough. Oh yeah, and you can play with Desmos. That's cool. But on my website, Math 141. All right. Oh, by the way, I do have the solutions up, and they're correct, except that I put that one of the problems was like 6 points instead of 5 or something. I have to change that. But the solutions are good, except for a point total somewhere, a point assignment. Old exams, quiz 1B. Quiz 1B will help. Okay, it'll help. Try it out without looking at the solutions. No one learns that way. Literally, students tell me they learn nothing if the solutions are anywhere near them when they're taking this as a practice run. I do have the solutions here, though. All right, so I have some homework requests. And put hi in the chat if you haven't done so already, right? Yeah, you're free to go so that people don't feel guilty asking questions. You're free to go. All right. Okay. By the way, pick a color if you wish. Also, did you have any particular comments about this problem? 1.45. I don't know what to do. Okay. Ah, yes. Okay. In fact, I did C before on the day 8 video. I'll go ahead and do A now. All right. Wait, what chartreuse is that? Is that a dark red? What chartreuse? Is that dark red? Oh, green yellowish. See, I don't know. Like that? Like that? All right. That's pretty cool. Okay. I don't know my colors. I'm not an art major. Okay. Want to do A or do you have a preference? C is on the video from day 8. Okay. So 1, 4, 5. I'll start with A, but if there are any others you want me to do, let me know. Okay. So 1 point. I don't want to trigger you. I normally put the list in blue. Okay, so 1.4 5A for now, and I see in there 1.34. Okay, so we'll do this now. I'll go ahead and open another thing here. Okay. I love my free whiteboards. Okay, so let's do this. Okay, this is 1.4 5A. 1.4 is on transformations. Okay, 1.4 is on transformations. We're doing 5A. All right, and I can do some of these others if you want. I did C on day 8. Okay, so if the for 5A, all right, 1.4. 1.4 5A. All right, if the point -4, 2 lies on the graph of y equals f of x. In fact, that could be the entire graph, just that point. All right, so let's see here. Okay, so the point -4, 2, basically here. All right. Okay. The only thing I know about this graph is that this point lies on it and it passes the VLT and all that, right? Okay, if this point lies on the graph of y equals f of x, what point must then lie on the graph of this transformed function? Y equals f of x plus 2 all minus 5. All right, so when we replace or substitute x with x plus 2, when we substitute x with x plus 2, what happens to the graph? What happens to the graph? Now, you see the plus, you might think we shift right. That's incorrect. The sign surprises you. We shift left. we shift left by 2 units. So because from here to here, we substitute the x with x plus 2 over here. I'll do this in red. We substitute the x here with x plus 2. That means that we translate to the left by 2 units. In particular, see, I don't know what's going on with this graph, okay? But this whole graph's going to go left 2 units. This point is going to go left by 2 units. To the point what? To the point -6, 2, because we subtract 2 from the x coordinate. I like, it helps me to draw the picture, all right? So now we're at the point -6, 2. But now I'll do this in dark green, okay? What about the -5? What does the -5 do to the graph here? The -5 has the impact of lowering the graph by 5 units. In particular, the point -6, 2 is lowered by 5 units. The x coordinate stays the same, still -6, but now we take 2 minus 5 and we get -3. So if -4, 2 is on the original graph, the point -6, -3 must be on the new graph. Y equals this guy over here. Okay. 1.4. 5a, yep, -6, -3. All right. If you get a problem like that on the test, you don't necessarily have to show work, but if you do show me maybe a little bit, maybe I could even give some partial credit, maybe. But yeah, I'd probably accept the answer only for this if I gave you this kind of question on the test. All right. By the way, there's another one in the chat here, 1.25c. Add that to the list. All right. Any questions? Any questions? 1.45a. All right, let's go to, what's the next one? 1.3, number 4. Okay, basic graphs and symmetry. Okay. So I'll do this straight off here. Why is it rare? Well, I can do this. So pick a color if you wish. Pick a color. 1.3, number 4. Pick a color if you wish. Otherwise, I'll pick purple. Right? Purple. Right? Why is it rare for the graph of y equals f of x to be symmetric about the x-axis? Okay. So give me some insight. I know that I have an answer for this in the sheets, but students, give me some insight on this. What do we know about the graph of a function where y is a function of x? It's got to do what? The graph has to pass what test?
The vertical line test.
The vertical line test. Okay. Now, what's the problem with symmetry about the x-axis? See, here's the thing. If you have any point on the graph that's off the x-axis, if you have symmetry about the x-axis, that point has to have a partner point on the other side of the x-axis. What's the problem?
It doesn't pass the test.
The graph would then fail the VLT immediately. Which means if you have y as a function of x, you better stay entirely on the x-axis. Do you know a function that does that? F of x equals what? 0. If you have y as a function of x, the 0 function is the only one whose graph is allowed to be symmetric about the x-axis. Okay, because that's okay, right? This is symmetric about the x-axis. It is the x-axis, and it passes VLT. But if you move even a little bit off the x-axis, it's going to get partner points on the other side. You're going to fail the VLT. That's why these are rare, because these graphs tend to fail the VLT. In fact, everyone except the 0 function is going to fail the VLT. That's why. Okay, a little tricky, but it's a good concept question.
Yeah,
Question.
I struggle with graphs, so thank you. That was very
Oh,
helpful.
you're welcome. Play with pictures. I know it's like kindergarten. Play with pictures. I gotta do it too. Play with pictures.
Yeah, I think it was in I think it's in 1.3 where it has like the graph with all the different types of well, it has all the different types of graphs, but it's
Where the basic graphs. Oh, now they're not all the functions, but they're the basic classic functions that I'd expect you to know immediately on
Yeah.
the test, right? Of course, you know it's point plot, right? You know it's point plot, but no, you should know graphs like y equals x squared, x cubed, square root. Yeah. So those are listed out in. Oh yeah, and know that gallery, right? So commit that gallery of graphs to memory to make things easier. Because trust me, you don't want to waste your 50 minutes point plotting. Trust me. If you have to, you have to, but don't waste your 50 minutes. All right. Any questions or comments here? Well, we're on 1.3. Anything else here? Okay, so 1.2 number 1.25c is next. What is that? Yes. Okay, so I'm going to need another whiteboard for this. Okay, so
Oh, teal, please.
teal. I love teal. Yeah.
Yeah.
All right. Okay. Oh, that chartreuse thing is pretty cool too. All right. Okay. 1.25c. All right.
Oh, quadratic formula.
Right. Okay. Okay. So this is 1.2, which is about graphs, right? Graphs. 1.2, number 5c. Okay. 5. For each of a to d below, find the x and y intercepts of the graph of y equals f of x. If they're none, write none. Okay. Now for c. Now, which is easier, by the way? Which is easier? X-intercepts or y-intercepts? Which is easier?
In this case, it's the y-intercept.
Right. Because what do? You plug in what equals what?
Oh, f of x equals y. Oh, wait.
For y-intercept, you plug in x equals 0. It's a plug-in. It's an evaluation. So f of x is y, right? F of x equals y equals the square root of 9, well, minus 0, minus 0, right? You're plugging in x equals 0.
Uh-huh.
And what's the square root of 9? The principal square root of 9
3.
is 3. Now, remember, technically, intercepts are ordered pairs. Is it 3, 0? Now,
I believe so.
well, careful. What's x? What's y?
Oh, no, it's 0, 3.
0, 3. But I make that mistake all the time. Yeah, I admit that. I often switch x, y. Yeah. Okay. So this is your y-intercept. Okay. But it's still easier to find because you get it by plugging in x equals 0. If 0 is not in the domain, then there is no y-intercept, like y equals 1 over x. But this guy does have a y-intercept. It's at 0, 3. That's the easy part. Now, the harder part is the x-intercept or intercepts, if any. I don't even know how many this thing has. Okay. Y-intercept 0, it's either 0 or 1 because you can't have 2, right? Because you got to pass a VLT. Okay, x-intercept or intercepts, if any. I have no idea how many this has.
Yeah.
All right. Well, what do? We plug in y equals 0 or f of x equals 0. Basically, you set this guy equal to 0, right? You set this guy equal to 0.
Yeah.
Okay, so I'll turn around. Root 9 minus 3x minus 4x squared equals y or 0, right? Y equals 0. Plug in y equals 0. Okay, plug in y equals 0 or f of x equals 0, either way.
Oh.
We want to know the real zeros. We're keeping it real. We want to know the real zeros of this guy. And yeah, this is pretty intimidating, isn't it? Okay.
Yeah.
But here's the deal. What's the only time that the square root of something is 0? It's if that something is 0. The only way that root blah is 0 is if blah itself is 0, right? These are perfectly equivalent. Okay. Questions. Remember, if you're finding the zeros of a radical, you can ignore the radical. Okay, just grab that radicand, set equal to 0. Okay, it's a leap of faith. All right. Now, here's the thing. There are two things I don't like about this quadratic. What do you think? There are two things I don't like about that quadratic, the way it's written.
Not in order, and
Right, it's non-descending powers,
yes,
and also the leading coefficient is
negative.
negative. Yeah, but you want to know a good fix for that? Either multiply by -1, or another thing you can do is that you can add and subtract to both sides, right? Let's add the 4x squared. Don't say move. Add the 4x squared, and then do what?
What? Okay, add the 4x squared, then subtract the 9. And
Okay,
then
subtract the 9 and
divide it by 3.
well,
or
we have a -3x here. How do I
Yeah.
get rid of it on the left? How do you get rid of a -3x?
you can divide it by, or multiply it by a -1.
Add 3x.
Oh,
And
you meant
yes.
that.
Yeah, I
Okay.
mean, yeah. You should pick your strategy.
I thought you meant
here, I-
isolate for X.
Okay, well, here's the thing. From here to here, you have two possible strategies. One is to do what I did here, which is to add or subtract, right? So that, and also I put it in the right, in a good order, right? Descending powers.
Mhm.
By the way, folks, I'm recording. Let me know if you want me to pause. Or another strategy, like you were hinting, you could go, you know what? Multiply both sides by negative. In fact, I'll do this. I'll put this in green. You could multiply both sides by -1. -9 plus 3x plus 4x squared equals, that's still 0 over there, right?
Yeah.
But that's fine because then you can reorder these and you get that polynomial, right? So
Mhm.
either would be correct. Okay. You agree that either would be correct. Okay.
Yeah.
Now here, I decided to do it this way because it was a way for me to get to descending powers immediately. Because as it stands, you see, this is confusing as heck, right? You want to basically rewrite this as this, whether the zero's on the left or the right, right? Okay. So let's go from here. And you're right. We're going to need what? You said it. We're going to need what?
Quadratic formula.
Yeah, because if you work out the discriminant, you're going to find that it's not a nice perfect square. Also, if you try to use the guess method or whatever, it's not going to work out. You're going to need the QF. It may help to write the parameters. A is 4, that's the leading coefficient. B is 3, that's the linear coefficient. Be careful though. What is C? Careful. C is
It's negative.
negative
Yeah.
9. A lot of people
Okay,
put 9. It's -9. Carry that sign. All right. And then it's a matter of remembering. You got to remember. By the way, folks, even if you have like a really nice scientific calculator, I'd like to see the work. I'd like to see the QF, or at least after you plug in the numbers, even if you have a good calculator. All right, let's do it.
Oh, negative b plus or minus square
The whole
root.
discriminant thing, right? Okay, I'll go back to
Ah.
C now. All right, so
Oops.
X equals,
Oh, am I supposed to?
okay, what's the quadratic formula? The
Oh.
opposite of B
Yeah. Plus
plus
or
or minus
minus
the
square root of
the discriminant. What's the discriminant?
b squared minus 4ac
Excellent. All over
2a.
2a. Now remember, it's all over. A lot of people shrink their fraction bars. Don't shrink that fraction bar, right? Nice long fraction bar. All over 2a, right? Okay, so let's go ahead and plug into this. I'll grab another whiteboard. All right. So we'll get this over here. All right. So we have X equals, okay, the opposite of B, that's the opposite of 3, plus or minus the square root of, okay, B is
9.
3,
Oh,
that's squared, 9, yeah, that's fine. B squared minus 4,
a.
A,
C.
and then C. See, I'm a klutz. I got to write things in first. So
Oh,
yeah.
yeah.
And it's going to show work anyway, right?
Yes.
Bear in mind, if you make an error, okay, it helps to show work if you make an error because then I can really give you partial credit. All over twice 4. Okay, this is not rhetorical. Did I write that right? Opposite of B plus minus square root of B squared
minus 4ac over 2a. I think this is right. Okay, we'll see soon enough. Equals. Okay, let's clean it up. Oh, wait, that's the opposite of, oops. Opposite of 3. The square's in here. Plus or minus the square root of. Now, this is 9
Yeah, and then
plus.
that one is
Uh-oh.
144, I think.
Yeah, 144. Okay. 144 all over 8. Now, it would be beautiful if this were just root 144. But remember, we couldn't factor that thing. And that's a sign that this ain't going to be a perfect square. It's going to be 153.
Yeah. And it's like 3 square root 17.
Yeah, yeah. And I give you a nice little number theory hint. It comes in really handy. The square root of 153 all over 8. And then you go, oh my gosh, how do I deal with that? Well, here's the thing. I give a key hint in my I give a key hint in the homework. See, here's a great hint. I'll put this in red. All right. If you have a positive integer, add up the digits in that positive integer. 1 plus 5 plus 3 equals 9. If the digits here add up to a multiple of 9, then this thing is divisible by 9. And then on your scientific calculator, it's 17. 153 is 9 times 17. But I love that number theory trick. Again, if you have a positive integer and the digits add up to a multiple of 9, the integer is divisible by 9. That's a great trick. By the way, that trick also works for multiples of 3. If the sum also adds up to a multiple of 3, and this is also divisible by 3. In fact, it's divisible by 9. Okay, so that was my hint. It's a great number theory hint. Equals, oops. Let's go back to teal. All right, so we have -3 plus or minus okay, the square root of, I'll write the 153 as 9 times 17 all over 8. All right, equals. You can skip from the top to over here. That's fine. This step in the middle is not necessary, but -3 plus or minus. Remember, by the rules of radicals, this is root 9 times root 17. What's the principal square root of 9?
3.
3. Oh, when we look at it, the 9 pops out as a 3, right?
Yeah.
3 root 17 all over 8. Now, if we had like a 9 down there, then we could do further cancellation. We could like factor a 3 out of there. But I know 8 is not divisible by 3. So I'm okay with this as an exact form. What's the question, by the way? Are they asking for the... Yeah, find the XY intercepts. So what are the X-intercepts? They're going to be at... the number with the plus sign, comma 0, because the y coordinate is 0, and the number with the minus sign, comma 0.
And would we need to write that part, or would it be fine if we just wrote the one before that step?
Oh, you mean this? I know a lot of books would write. Well, first of all, if I ask you for an intercept, you should put the comma 0, right? Technically. But the thing is, the plus minus can be sometimes ambiguous, right? Because like especially in trig, it gets confusing because sometimes we don't know if we have to choose or if both apply. Plus minus can be ambiguous. So that is one issue I have with it. The ideal is to actually list them out, the plus case and the minus case. That would be ideal. But let me see how I did it in my homework.
I believe it was just you left it as is.
Yeah, because I was probably kind of lazy there. It's probably more proper to separate. And on an exam, I'll know what you mean. Yeah. I was kind of lazy. I didn't want to separate them out. Okay. We kind of assumed that you take both. Now in Calc 3, right, then it gets a lot more confusing. Wait, do I pick one or take both? Even in trig. But yeah, I was kind of lazy here. Yeah.
Okay, both of these are X-intercepts. There are two, both the plus case and the minus case. Okay.
Oh, okay.
And if you wish, you can do a decimal approximation on your own. But remember, in a math class, we tend to prefer exact answers, except maybe for word problems.
Oh,
Okay. But anyway, I think the question was, how do you simplify root 153? Yeah, and that number theory trick helps a lot.
yeah.
All right.
Thank you.
Oh, you're welcome. Yes. So a lot of this was getting down to the nitty gritty, right? That algebra and these number theory tricks. Yeah. Okay. So was there anything else in chat? Let me see here. Okay. Well, it's 9:42, but I'm willing to go on. I'm willing to go on at 10:30 if you want. But then we have to watch the Daily Show, don't we? I'm kidding. But I probably will. But any more questions? Okay, go ahead and take a look at your homework. I'll wait. So let me know if you have more questions. At 9:45, I'll check on you. It might just be a matter of starring or highlighting the homework problems where you have difficulty and kind of scanning over them before the exam. Don't do new learning too soon before an exam. It's a matter of, well, what problems do I need to review? So the homework went well. That's a good sign. I hope you've done the homework, right? I hope you did it and you found it easy. Okay. You should be that
Some
far.
of it. Some of it's easy.
Okay. But now's the time to ask me about the others. Are there any others that are kind of tickling your brain, or now's the time? I'm here.
For this one, this same question I asked earlier, I actually ended up with a slightly different answer where I did the quadratic formula correctly, but then I ended up with a -8 at the numerator, and I got quite confused with that. And I
Wait,
was
a
wondering,
-8 in the numerator?
yeah.
Can you describe for me one of your steps?
So
What'd you get?
okay. So I got 3 plus or minus the square root or 3 plus or minus, wait, yeah, okay, 3 plus or minus 3 square root of 17 over -8.
That's perfectly okay. You know why? Because if you basically see the guy down here, hypothetically, I'll do this in purple. If you multiply, I'm gonna shrink this. If you multiply top and bottom by -1,
Yeah.
okay, then the -3 becomes a +3. Plus minus stays plus minus. Sticklers would do this, but I'm not going to bother. But you know, but basically plus minus stays the same, right? Plus minus goes to plus minus 3 root 17 over -8. -8, right?
Oh, yeah.
Full credit. I say full credit.
Oh, okay. Because like you can like the fraction rule where you could put the negative in the middle or like on top and it will be the
Well,
same.
here's a way to look at it. You agree that we can multiply by -1 over -1. You're multiplying by 1, right? And the -1 distributes through the top. So the -3 becomes +3, plus minus minus plus, same thing, right?
Yeah.
3 root 17 all over, now -8. I would give this full credit. Now your calculus instructor might prefer if you you know, pop out the negative. They might prefer that you pop out the negative sign maybe, but I'm fine with that. I'm thrilled.
Oh.
If you can get up to here, I'm thrilled. Again, comma the 0, right? Comma 0.
Yeah.
Yeah.
Thank you.
Generally speaking, yeah. So again, if you have like a -8 down here, it's usually preferred to pop out the -1 factor. But in terms of this versus this, you know, books tend to want to minimize the use of this symbol. But you know, if you're correct, that's great, right? Yeah. Oh, No, 1.11 is not required. Although if you think about it, it's not too hard, right? Basically, to take the derivative, you let h approach 0. And, that's a good mind problem. You're right. You don't have to do 1.11, but that's the easy part. 1.10 is the hard part. 1.11 is the easy part. And hey, in 1.11, if you can do that, you can say, hey, I've taken derivatives. I found derivatives. And yes, there are shortcuts. There's some shortcuts that some of you already know from a high school calculus class, but you got to start with the theory. You got to start with the difference quotient. All right. Any questions? So I'll check again at 9:49. Did you get everything else, or would you like to go over one of the difference quotient ones? Or I'll have online office hours Wednesday, but please try to email me first so I'm aware. Thursday, I'll be in my office. MS 2:15 p.m. on Thursday. Was it 5:30 to 6:45 p.m. on Thursday?
Do you know how early the library opens?
Oh, do I have that information? Let me check. LRC.
Because I was thinking about coming in at like 6 in the morning, like that day.
You're dedicated. I don't think it's as early as 6, but let me see here. LRC. It's called the LRC, the
Oh,
Learning
yeah.
Resource Center.
Yeah, I hope my grade's good this time because I've too much time put towards math. So
Okay, so it says here Monday to Thursday, 9:30 a.m. to 5 p.m. That's kind of stingy for a library, but bear in mind that we have staff and some of them might be online still. But yeah,
Yeah.
Monday to Thursday, 9:30 a.m. to 5 p.m. I think they were trying to get something Friday and Saturday. Also, there's virtual
Oh, yeah.
virtual help. But are you talking like meeting with students, right? So yeah. So
Oh, I mean just like loitering inside the library while studying by myself.
yeah. Oh yeah, yeah. So that well, basically live, right? So yeah. So you don't need video with yourself, right?
Yeah.
Yeah. So I'm so handsome. No, there's a reason why I don't put my video on because I'm wearing a t-shirt right now. But okay, I should probably cut that out. But yeah, it says here, and this I got this file August 18th. It says here Monday through Thursday, 9:30 a.m. to 5 p.m.
Yeah.
Yeah, I remember they closed at 5 p.m. because a bunch of guys came to my office around 5 p.m.
Oh, I was one of them.
Yeah, right.
Yeah.
And that's okay. But the thing is, I usually like eat something around there. So
Yeah.
But hey, I mean, you can work and then 5:30, that's fine.
Yeah.
Yeah.
Thank you for the information. I shall
You're
use it.
Yeah. Okay, so I see a request 1.10 number 4. All right. I think that's one of those difference quotient ones. Okay. All right. While we're at it, yeah. Okay, so if you wish, pick a color. Or if you have any comments about this question. All right, 1.10, number 4. All right. Okay, so let's go. Oh, okay, orange. Orange? All right, whoops. Sounds good. All right. Oh, nice. That's a nice bright color there. All right. 1.10, number 4. I'm still recording. Let me know if you don't want me to, but I'll post this on the website. I'll post this on the YouTube playlist, the whole class video. All right. Let f of x equal 1 over x. Simplify the difference quotient completely. And on an exam, I'll remind you that this is the form I want. So you won't have to memorize this form. Now, for average rate of change, you have to remember how to do average rate of change. But this formula I would give to you over here. By the way, f of x plus h. When you see that, I'm telling you f of x is 1 over x. When you see f of x plus h, what S word should you be thinking? You should be thinking substitution. Substitute the x with x plus h. That's critical. All right. So what's the deal here? And some of you might even profit by writing this separately. You don't have to, but substitution. 1 over, not x, but x plus h. F is the reciprocal function. It takes the reciprocal of its input. The reciprocal of x is 1 over x. The reciprocal of x plus h is 1 over the denominator, x plus h. It is not this. A lot of people are attempting to do this. That's wrong. Okay? It's a substitution, not a straight addition out here. So what's this difference quotient? F of x plus h. What a big line here. F of x plus h minus f of x all over h. Don't worry about the domain issue here. Equals, all right, f of x plus h is 1 over x plus h. That's a critical observation. Minus f of x I gave you, that's 1 over x. All over the h. And the question is, do you now know how to simplify a compound rational expression? There are two options, two key options. One option is that you can basically multiply by the LCD, the product in this case, over itself. You're multiplying by 1 again. Don't worry about domain. Or you can try to make one fraction on top here. What is your preference? Would you prefer the method on the left, the method on the right? Would you like to see both? Any preference? Method on the left, method on the right. Any preference?
Probably on the left.
Left. Okay. I tend to like that too because I like the idea of clearing fractions early on. Okay. But you can choose either. Let's do the method on the left. All right. I'll go back to orange. Okay. Equals. All right. I'm going to copy what I have over here. For good measure, I'm going to put grouping symbols. The fraction bar automatically groups the top, but I think visually this will be more appealing. 1 over x plus h minus 1 over x all over the h times the overall LCD, which I'll put in red here. The overall LCD here is the product of the two denominators, x multiplied by the factor x plus h. The idea here is that we want to multiply by 1, right? So if we, okay, right. So if we multiply the top by this junk, I can multiply the bottom by this junk. I often forget to do that. In fact, the part where I really forget, of course, you probably have a better memory than I do, but equals. First of all, on the bottom, it's the h, the x, and the x plus h. Don't forget this piece. Remember it. If you multiply the top by x and x plus h, you have to multiply the bottom by x and x plus h. Again, don't freak out about domain for this problem. All right. On the top. Now, don't just go boom, 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 boom. I'm thinking what D word? Distribute. Very good. The distributive property. I agree. Okay. and you distribute before you go strike, strike. All right. But I will write it out. You don't have to, but for clarity's sake, I'll write this out. We have 1 over x plus h times both of these, x and x plus h, minus 1 over x times, once again, the x and the x plus h. All right. And tell me what happens in the top. What happens? Yeah, we have a bunch of cancellations. I'll do this in red. Dark red. Okay. X plus h divide by itself. We have ones here. All right. Here, it's the x's that cancel out. Okay. So what are we left with on the top? We are left with plain old x minus, we have the x plus h, and I've made a mistake here. I've intentionally made a mistake here. It's a common student error. What am I missing on top? What am I missing? A lot of students mess this up. X minus grouping symbols. Okay, remember the x plus h is grouped here. And the -1 applies to both these guys. All over that product down there. H, x, and x plus h. Don't strike these yet. Anytime you have 2 or more terms, don't do top-bottom canceling. That's very dangerous. All right. Any questions? Let's distribute the -1 over here. We got x minus x. What? It's x minus x minus h. All over the product. H, x, and x plus h. Question so far? Question so far? I think we can squeeze the rest down this column here. Equals. All right. What happens on the top? Who's left? Who's left?
X minus h.
X minus x goes bye-bye. That's 0. We have the opposite of h over h, x, x plus h. I often forget those pieces there. By the way, for a problem like this, if you get an answer like 1 or -1, you probably messed up. Okay. Hey, what can I do? What can I do here? I'm not done yet. The goal is to simplify. What can I do? I'll do this in green. What's opposite h divided by h? Basically, what's -h divided by h? -1. I'll put a -1 here, put a 1 down here. All right, that's an equal sign over here. All right. Equals. It's a -1. And we normally pop out that negative sign, -1 over x and x plus h. There's a hidden restriction, h cannot be 0, but there were also other restrictions to the domain. For example, x cannot be opposite h. X cannot be 0 for that matter. But hey, I'll be thrilled if you get up to here. In calculus, we can find the derivative of 1 over x, that function, as we let h approach 0. What do we have here? If we let h approach 0, we have the opposite of 1 over x times x is x squared. The derivative of 1 over x is the opposite of 1 over x squared. But see, the calculus there was the easiest part of the problem. This is the harder part. Any questions? Any questions? Any questions? All right. Yeah, yeah. It's always good to do it yourself, like blank sheet of paper, right? Okay, so I'll check on you at 10:03. And thank you for your perseverance, by the way. I'm impressed by your diligence, hard work. Got to give you credit. It's late. Yeah, I'm getting up pretty early too, because I've been crashing after classes. I'm wide awake. No, it's been going pretty well for me. I'm wide awake during class, and then after I upload those YouTube videos, then it's bye-bye. My sleep schedule is actually surprisingly normal nowadays. I used to go to bed at 5 a.m. All right. Any questions?
This is a fast one. It's 5D actually.
Which section? 1.1?
Oh, 1.2.
1.2.
I have done it already. I just forget why something happens.
1.25
Yes, D.
D.
Yes.
Okay.
So yeah.
All right, let's do it. This is we're finding the intercepts again, right? Again, the y-intercept is going to be what, 0, -1. That's pretty straightforward. It's the x-intercepts, of course. Okay, pick a color if you wish.
Teal.
Teal again, I love teal. That's
Yes.
okay.
I like it too.
All right, let's get another
That's
one.
that's actually the question I had. Like, how did you get -1?
Oh, I'll do that in a minute. Yeah, so let me grab the y-intercept. Yeah, okay. So okay, so 1.25D. First, y-intercept. Okay, so that's when you plug in what equals what? You plug in x
Oh,
equals 0, because the
Oh, yeah,
y-axis
that.
has equation x equals 0. That's where the x coordinates are always 0. All right. It's almost like we're solving a system. All right, now we're saying x equals 0. So we have f of 0
yes.
or y, equals. So you agree on the top we're gonna get 0. You don't have to write 0. 0 plus 0 minus 4 all over 0 plus 4. Okay, you don't have to write the zeros, but what do we get? We get -4 over 4, which is
-1.
-1. Yes, don't forget the bottom, right? -1. Technically, the y-intercept is a point, so it's okay. Careful. The x coordinate is 0, and the y coordinate is
1.
-1. Yeah, that's the sole y-intercept.
Oh, yikes.
And bear in mind, we have y as a function of x. You can only have one y-intercept. Can't have 2 or 3 because you'll fail the VLT then.
Yes.
Yeah, and if 0 is not in the domain, then there's no y-intercept. So you either have one y-intercept or nothing at all, right? Questions? Questions? Let me check the chat. Yeah. Remember, it's -4 divided by 4, right? Now, x-intercepts, I presume that you're also asking about the x-intercepts, right?
Oh, not really. I already finished it, and that was correct.
Yeah, you factor, and I don't know if the -4 is eliminated or whatever, but wait, what's going on?
It is. One of them is eliminated because if you subtract 4, it cannot, like, x cannot be -4.
Yeah, I see that there's one x-intercept and not 2, because I think x plus 4 is a factor, which means -4 is not in the domain. You cannot have an x-intercept if the x coordinate is not in the domain.
Yeah.
So that's the problem. Yeah. Okay. So you understood that. Oh, by the way, for people's benefit, because maybe other people didn't get that. So let's say we want to find the x-intercept. The x-intercept or intercepts, if any. X x-intercept or intercepts, if any. Okay, you have to be that much of a stickler, but all right. Okay, now that's the hard part. You gotta set this whole thing equal to 0, right? So
Yes.
that guy, I'll say star, star. You put star on the test, star equals 0. All right. So when does a fraction equal to 0? At the very least, we need the top equal to 0, right? We need 5x squared plus 19x minus 4 equal to 0. And the bottom cannot be 0. Well, basically, x has to be in the domain. And the only domain problem we have to worry about is the idea of division by 0. So we need x plus 4 to not be 0. In other words, x cannot be -4. So if we come up with -4 as a tentative 0, we got to nix it. We got to reject it because of the domain issue. This actually factors old school, although I wouldn't blame people for using the QF, but this does factor old school. 5x and x, split signs. 19x, that's pretty heavy, right? So I'm thinking 5x times +4. The -1 over here.
Mhm.
-1 times 4 is -4. 20x minus 1x is 19x. Okay, because the 5x times 4 is a nice heavy 20x. Then we have the minus x in there. ZFP, do you know what ZFP stands for? ZFP is a zero factor
Oh,
property.
I've never heard of ZFP before, but zero factor property is definitely familiar. That
Yeah.
abbreviation isn't.
The only way the product is 0, yeah, I'm like a military guy. It's like, okay, the only way a product is 0 is if and only if a factor is 0. I'm assuming everything's well defined. They are. Okay, so we have 5x minus 1 equals 0, or x plus 4 equals 0, right? Over here, solve for x, 5x equals 1, adding 1, don't say move. X is what?
X is 1/5 or
1/5, right? 1/5, which is not -4. Okay, so it looks like 1/5 comma 0 is good to go as an x-intercept. Subtract 4, x equals -4. What's the problem with this guy?
it makes it 0 if you plug it in
Yeah, it makes what part 0?
the denominator, and it can't be.
Right, correct. And you're not allowed to divide by 0 ever, 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 even in complex variables. All right, so we got to reject this part. Still, show me that work and show me the rejection. Like a bad romantic comedy showing the rejection. But remember, x cannot be -4. You'll get a 0 denominator. Again, for a rational expression like this, right, this fraction, when does this fraction equal 0? If and only if the top is 0, but the bottom is not. That's a domain issue.
Oh yeah.
And this is the sole x-intercept. Box that in. Okay, it's good to box in your final answer.
Would a circle be fine? Circle's fine, right?
Well, it's the only one. I mean, when I do my work, I often circle key information and I box in my final answer. But basically, make it clear to me that you're indicating your final answer clearly. Be clear. That's the
Okay.
main thing.
Just make it very bright. Okay.
Yeah, yeah. And if there's something that is off to the side, cross it out. Don't erase it. Okay, because it might be worth some points, but don't be ambiguous. I mean, make sure don't give me two different answers to your problem. All right.
Oh yeah.
It's okay to have two solutions, maybe, but don't give me two different answers, right?
Yeah.
To do that, you got to cross out one, so you at least tell me what your preferred solution and answer is. Yeah.
Yeah.
Okay. Any questions there or anything else? Okay, I'll check on you at 10:12. Any questions?
How was your evening? Oh.
I'm doing pretty well. I'm glad I had some chocolate during the break. Chocolate tends to keep me awake. So, yeah. Yeah. I mean, I enjoy math. I enjoy teaching math. It's just that, as a student has noted in chat, yeah, we've been up since early morning doing stuff, just doing stuff. I had to write your exam, right? I had to write your quiz 1B.
Oh yeah.
That's what I spent most of my day on. so that you'll enjoy it. Oh, okay. So there's a question in chat. 1.2, number 6. Why is 1.26? Oh, are you talking about the bracket issue? Because that confuses instructors too. Are you referring to the bracket issue? You said 1.2 problem 6, is that correct? 1.2 problem 6? That's this. Oh, now the graph looks like that, right? The graph looks like this. And when we refer to intervals of increase and decrease, we're talking about intervals of x coordinates. So for example, here, I'll do this in red. Okay, so the function is increasing from negative infinity. That's not a number, but parenthesis negative infinity, comma 0. Technically, we put a bracket because if you consider this piece of the graph, it's true that if you take any two distinct points, the point on the right will always be higher than the point on the left. And that's true even if you put a bracket near the 0. Here you're decreasing on the interval from 0 to infinity. On an exam, I would not penalize for putting parentheses because there's some confusion on that. Nine. Okay. Remember, these intervals of increase or decrease, they're referring to x coordinates. 9 comes up if you're talking about the range, right? Just out of curiosity, explaining curiosity, the range would be this. That's the range. The intervals of increase and decrease are always subsets of the domain. The domain is all reals here. Yeah, I'm trying to see. 9 comes up if I wanted the range. Okay, I see now what you're asking. Questions? Sure. Domain versus range. And the intervals of increase and decrease are subsets of the domain, x coordinates. 10:15, I'll check on you. Oh, questions? Oh yeah, I keep them. Because sometimes we might refer back to them. I've what, 4 terabytes of memory on my MacBook? Why not? I like to save my work. I'm a real pack rat. One reason I don't put the video on, if you were to see my room, oh, it's a cluttered mess. There's boxes on boxes. At least these whiteboards are compact.
Do you have a NAS by any chance for just your whiteboards?
I'm sorry, do I have a what? A NAS?
Yeah, network attached storage.
No, I don't know what that is. These are just preview. These are just preview documents on my MacBook.
Oh, it's essentially like another system running on your thing that you could transfer files to. So like it keeps it off your main computer.
Oh, well, no, I mean, I still have like 2.3 terabytes left on my laptop, so I'm good. Yeah, these don't take that much space. Take up that
In
much.
your laptop. Wow, that's wild. Okay.
Yeah, memory is amazing, right? All these
Yeah.
new chips. All right, I'll wait another minute as people kind of look over things.
I remember. Oh yeah, back in the '80s when I was a high school in the '80s, I had my Apple IIe with 64 kilobytes of RAM. It was so cute. Programming in basic.
Kilobytes. Yikes.
No colors, monochromatic screen. Just programming my little Card Sharks games. And
Yikes, must have been a brick.
bricks, yeah.
That's basically the size of a brick
You-
or
you play,
bigger.
You can play Breakout. I love
Oh, yeah.
Breakout though. Yeah. They had cute games. They were clever. Electronic Arts. They had some fun games. I couldn't play something like Call of Duty. Games are so complicated nowadays.
Oh yeah.
I love Breakout, the old Atari games, right? Like Breakout or Kaboom, Low Res,
You
Ready
can
Player One.
you can get them emulated on your computer and it's gonna be actually better than back then.
Oh yeah, yeah. I'm sure I could play those games online. Yeah.
Oh, I mean on your system, like running it on your MacBook.
Well, they were Activision games, for example, Activision, Electronic Arts. So emulators.
Yeah.
Hmm.
I mean, not for Call of Duty and all that, but I mean like the classics. Yeah,
Yeah.
you can definitely run them on like old hardware. I mean new hardware, but old hardware.
So you mean like people actually programmed them? Right.
Well, they sort of like rip it off the original game cartridge and then they import them into like a ROM file.
Mhm.
Then they make an emulator that can run it. Yeah. Gaming community. Pretty nice.
Yeah. Well, I guess Atari's not really around anymore. Who's to sue? Who's there to sue?
I mean, yeah, you could go to Japan and get like the cheap consoles there. Like,
Uh.
yeah. But then the plane ticket costs more. Yeah, never mind.
Yeah. I miss those games. Yeah, I'd like to do that someday. Play some old Kaboom, some old Breakout. I miss the Atari 2600. Again, I saw Ready Player One, right?
Oh yeah, that was a good movie.
Yeah.
Like 2017.
Actually,
it?
I just recently saw an anime that was a lot like that. It's called Sword Art Online.
Oh, that that was a good
Yeah.
anime.
I enjoyed it. Yeah. I mean, it's corny, but I mean, I know it's a popular one, but it's got good energy to it. Yeah.
Oh, you
That-
watch anime? No way.
I watch anime. Yeah. Well, yeah. Actually, a friend of mine got me into it. Got me back into it recently. But yeah, I've been watching. I like. I've been watching. Gosh, what have I seen lately? I've seen. Was it Death Parade? I've seen Death
Oh,
Parade.
Death Parade's good. Yeah, that one
Yeah.
actually doesn't have a manga. It's
Oh yeah, right, right. I've seen. Oh, what was one that my friend liked? It was Mob Psycho 100. That's
oh, Mob Psycho has also really good animation. Yeah.
yeah, yeah. Do you have other favorites? Others you'd recommend?
Right now I'm actually watching Neon Evangelion,
Really?
the 1995 one. Initial D is also pretty good. That was also an old anime. It's about cars.
Mhm.
One you might like. What type of genres do you like? Sort of, yeah.
And by the way, this is recording. Let me know if you
Oh
want,
yeah.
want me to trim this. But well, you know, let's see. Well, as far as manga goes, I mean, I love Battle Royale, the movie, and I got
Oh,
the
yeah.
manga for that too. But that was very violent. But yeah, like I said, a friend of mine just got me back into anime after a while. Well, I mean, because it's the thing is, I only recently got a smart TV, and it's like,
Oh.
like this year, I got a smart TV, and I'm able to watch a lot of good stuff in background while I'm grading, right? Things like that.
Uh-huh.
So that's helped a lot. Just being able to multitask, right?
Yeah. There's a really heartwarming anime called Keion, like Keion. It's like, yeah. Yeah. Man, a professor liking anime. Geez, I've never heard of that.
Well, I mean, Japanese American, so it's not so surprising. Although I don't know Japanese though, but
Oh.
yeah. So I can't say that culturally I'm very Japanese. I don't eat sushi, for example, but
Yeah,
Everyone
it's not.
else
That's,
eats sushi but me. I like Mexican, but
actually, food's
but
good.
but well, yeah. In terms of what a stereotypical Japanese or Japanese American person might do, I take lots of photos. Like in Vegas, I'm always there with my camera, like my iPhone, taking photos of everything in Vegas, right?
Yeah.
And well, I like katsu. I like Japanese katsu.
Oh, like wait,
And
chicken katsu or
chicken
what?
katsu.
Oh,
Chicken katsu,
yes.
yeah. And I like anime. Yeah. When I was growing up, yeah, I remember watching some anime growing up, and I was on and off. But the thing about the series is that I didn't know how to watch this background, right? Being able to watch this background while I'm like grading or whatever. But ever since I got the smart TV, it helps a lot. Um, I watched High Rise Invasion.
Oh, that's
On my
good. Yeah.
laptop. I watched it on my laptop. So I reserved a corner of my screen for that. Yeah. But I'm able to multitask now. So
Well, if you want, like, I'm not meaning to plug myself in, but like, if you need anything smarter in your life, just like ask me. Technology is my technology.
oh, good, good.
Yes.
But and any anime recommendations? So K-On, is that it? Yeah,
It's here.
yeah.
It's
Oh, by the
like,
way, any other math questions?
or it's like
Right.
like this in American, but like, yeah, it's also on Netflix. Yeah.
Yeah. What else would you recommend?
Like, do you like dramas or like no drama, like violence, like
Oh,
it's like lots of violence, good violence.
anything good. I like funny ones too. Right.
Have you watched what is this, One Punch Man?
Oh, I had another friend who recommended that to me too. One Punch Man. Yeah.
It's really good. There's also this season, if you want some anime stuff, there's a thing called My Anime List. It's like the biggest database in America, or in North America at least.
Oh,
It's like updated everything. Very good community. Uh,
yeah. I just started subscribing to Crunchyroll. That's
oh
why.
yeah.
Yeah.
There's Bungo Stray Dogs. That's a pretty good one.
Yeah. Thanks a lot. Now, I should ask again. Any math questions for?
Oh
any-
yeah. Oops.
Yeah. There's only one other person, right?
Yeah.
Any questions? But it's good to have a break. I know I like chatting with the students.
It's nice to know what the professor likes as well, because you don't really talk to the professor much. It's more like do your homework and finish this test, and that's pretty much it for most people.
Yeah, yeah, yeah. I don't get much time to do stuff. I mean, I read news items and all that, but no, I was gonna see one reason why I started watching anime is because this friend of mine got me back onto it, but also I was watching too much news. I used to have news on the background, but then news gets depressing sometimes. So
Oh yeah, like recent events.
yeah, so it's like when I don't want to watch the news, like with like Afghanistan, right? Seeing Afghanistan unravel, that's so depressing. So I was like,
Yeah.
you know what? I'd rather watch some anime.
Yeah, yeah.
So that's when I saw Death Parade. Do you know anything like Death Parade? Any anime like that?
Like dark. There's hold up. I don't remember the name. It's, I think, Beautiful Bones on Hulu. It might be on something else.
Beautiful Bones. Huh. Anime so crazy. I love it. Anime so crazy though.
Yeah, it's like movies, but like anime. Yeah. There's one that's coming up recently. It's like, I don't know how to pronounce this. This one's like a slight horror.
Huh.
Yeah. There's more horror. It's that. I think the people watching this later is just going to be like, wow, nice anime recommendations for those who watch at least.
Yeah. So for people who are watching the video, if for those who watch the video and you're still bothering with this, see Beautiful Bones, Miruku-chan, and Shiki. All right.
Yeah.
Okay.
Oh, I think, yeah, the last guy finally left. Or not
So for
final.
those of you watching the video, yeah, I guess you stick around for the anime recommendations. Okay, well, that's fine. There'll be no anime questions on the test.
Do I email you? Like, do I email you more recommendations? Because
Sure,
like,
sure. I mean, feel free to communicate with me, email. Yeah. Like I said, I just started getting on a few weeks ago. Yeah,
well, I'm just going to like send you like a whole list one day.
yeah. I mean, the
If
one
you
thing I
have-
like about both Death Parade and SAO, Sword Art Online, is that I like the anime that are more disciplined and structured. Maybe because I'm a math person, right? So there's
Yeah.
I like ones that there's a logic, right? Like Death Parade had a bunch of at least some logic to it, right?
Yeah.
At least some idea of a procedure. Because you know how anime can get really random sometimes, right?
Yeah.
You know, Battle Royale wasn't an anime, but it was a movie and a manga, and there was a structure to it. I'm used to watching like those slashers, right? It's like they start with like 10 people and it goes down to one, right? And
Mhm.
Battle Royale was like that. And
Have you watched the SAO spin-off, which was what was it? Gun Gale Online, which was like a spin-off of SAO.
well, now there are 3 seasons, and that was season 2, right? Wait,
I think it was adaptation, like a side story.
Oh, okay.
Yeah, so that one is also it. And then there's one that's called Berserk. It's also, I mean, they ruined the animation, but it's still pretty good.
Berserk, is that based on SAO or?
No, it's a completely different one, but it's like, I don't know, it's like rated R, but like not really.
Uh-huh.
I don't know. Parts like anime, it doesn't seem rated R to me, even if it's a rated R. So
Yeah.
it's
Uh,
not.
You know, with SAO, I just finished watching the 3rd season. I really enjoyed the 3rd season.
Yeah, there it was. I liked it. The story was pretty nice.
Yeah, and the theme song is very catchy. I've been thinking about the theme song a lot. That's been running through my head.
If you like catchy theme songs, there is one. There's actually multiple. There is one about it's like an isekai, a guy reincarnated. Uh, it's is it Tanya the Evil? It's pretty good, I guess. Yeah.
Tanya the Evil.
Saga of Tanya the Evil.
Oh,
It's yeah. Uh, yeah. The 2nd season, pretty good opening. Wait, are you for SAO, are you on the arc where it's the world tree, arc where they're fairies, or is it I forgot which one, season
the
3?
3rd one is about the medieval society, and it's the one with the integrity knights and the axiom.
Oh, that one. Okay, the one after. Okay.
Yeah,
That one
it-
was pretty good, yeah.
Yeah, it felt the most like a coherent video game, right?
Yeah.
Yeah.
You just finished it, right? I'm not
Yeah.
gonna spoil anything.
Yeah. So those who are watching the video, right? Yeah, watch out.
Yeah, that's if you don't cut it out. You could just cut it out. This is like this might be a little awkward, sort of. I don't know. Maybe.
Well, people can choose to cut out. That's fine.
Yeah. Sorry, do you want more anime recommendations?
Sure, why not?
Yeah, I mean, I don't know when to stop, but like I'm also doing assignments, but I also should sleep soon, so I don't sleep early anyways.
Oh, I mean, I don't want to hold you up. No, I'm just saying that if
Oh.
there's anything that you're really excited about. that
Oh
you
no,
want-
no worries. I don't sleep, period. I mean, I rarely sleep because of homework anyways. I'm done with all of it, just so you know. It's just
Uh-huh.
studying again. Another anime. There's one called To Your Eternity on Crunchyroll. I don't want to really hold you up either, to be honest. Like if you need to go, just
Oh,
yeah.
no, I mean, you know, it's good to have these on background. Well, generally speaking, where do you watch these? How do you watch them?
Crunchyroll. I have like
Crunchyroll?
all the stuff to watch it on, so I mean, I don't really have time because I'm stressed about studying, which sucks.
But you know, sometimes these things, like if it's in background, if you're not too distracted by it, it's okay to have it on his background, just to, if it helps keep your sanity, right? So, but the thing is, you have to kind of judge it, right? And it's different for
Yeah.
different people. Some people get too distracted, right? But
Yeah.
other people, it's like, hey, it helps to have something on just to keep me sort of entertained almost.
Oops. Yeah, this is a comedy. It's actually fairly hilarious. Yeah, and you could watch Berserk on Crunchyroll as well. You might like Enin Shabotai, which is a Fire Force, which is also pretty good. Sorry, I don't have anyone to talk to about anime, so like you're gonna just get a lot of stuff.
Well, I'm sure there are some people in the class who enjoy it. Yeah, lots of people enjoy anime. Yeah, I've always enjoyed it. It's just the idea of getting into a series, right? It's like, oh, that might take up some time, but no, I mean, I can put things on it as background, and it helps me keep my sanity without making me inefficient.
Oh yeah.
Yeah.
By the way, this one, the Certain Scientific, it's a whole series. There's like 7 seasons. It's really good. It's still going. What else?
All right. Well, thank you. I think these will keep me plenty
Yes.
busy.
Yeah, I
Oh,
should
oh,
yeah.
Yeah. So yeah, anytime we want to bring it up, that could be like our after class discussion. And
Yeah.
we even keep recording for people's benefit. Maybe we can review them.
Yeah, for sure. If I have time, yeah.
All right.
Yes. Thank you.
Okay. Well, thank you. Any math questions? Anything else?
I think that's it until I bug you in person, because this is like stressful. Yeah.
We'll try not to. Well, I know some people actually thrive from stress, but most people don't. So, hey, yeah, seriously, you might want to have an anime in the corner of your computer screen, or I mean, you want to be able to psychologically put yourself in a good place, right?
Yes.
Without distracting yourself. So, yeah, I'm not suggesting that binging on anime is necessarily good for studying, but
Yeah.
if you can manage to keep it on his background, basically, in fact, you might even go back to old anime. Maybe old anime you've already seen, right? Where you're not so compelled by the storyline anymore. It's like just having a background, right? Like I might have some old horror movies I've seen plenty of times on background, and
Yeah.
I'll only pay attention on the scare scenes.
Yeah.
We all study different ways, yeah. But it's
Yeah.
not always a matter of just focusing on your computer screen or the book. Take a walk, maybe watch a little bit of something, or keep it on
Yeah.
his background. We have different styles, and you want to keep your sanity.
Yeah, hopefully I'm still sane by the end of this.
Hopefully, we all are.
Yeah, hopefully.
Well,
Yes.
again, thanks a ton. I mean, I hope that I'll be able to enjoy these in background as I work. Right?
Yes.
Yeah, I appreciate it.
Thank you.
All right, all right.
Yes.
Okay, so you want to call it a night?
Yes. Thank
All
you.
right. Thank you. Good luck, and I'll see you Thursday certainly.
See you Thursday.
Okay, take care.
Take care.